Okay, ladies and gentlemen, thank you very much being with us at this session. We should start. We are 3 minutes after 2 o'clock. First of all, I want to introduce myself. I'm Ioan Silviu Doboși. I'm the president of Romanian Building Services Association, and I'm very happy to be here with you. It's more than 20 years. Then in every December I coming here in Belgrade, and I want to congratulate also Professor Branislav Todorovic and Bratislav Blagojevic for this kind invitation, and also I want to congratulate the young generation who today organized here the conference. I want to mention here Marko Ignjatovic, Alexander Anđelković, Milena Blagojevic, and I think it's Tamara Bajic. It's the young generation. We are here, the generation who continue the tradition, but I want to mention them because it's very important. Let's switch direct in the program. The first presentation, it's name, challenge and problems of KGH in shopping centers, and the presentation will be done by Milovan Živković. Yes, please, the chair is yours. Thank you very much. May I have also yes, thank you. Okay, thank you. I want to thanks to our colleague Mihailo Vasic, yes, and also Professor Đinić, yes, yes. I know the pronunciation. I want to.
Ako postoje slušalice ovde za prevođenje sa srpskog na engleski jezik. Ne samo jedne, nego za profesora Balarasa i kolegu koji sedi.
Also, I need also. Yes, thank you.
Kolega, još nabavite par komada.
It's okay. Let's start. We manage.
Thank you. Koleginici i kolege, ja ću danas da govorim o problemima koji se dešavaju u tržnim centrima. Pošto je vreme jako kratko, morat ću ja vrlo brzo da izložim ovo predavanje. Projektovanje i izvođenje tržnih centara, ajde samo da slušalice stave. Projektovanje i izvođenje radova, KGH radova u tržnim centrima je vrlo složeno i tržni centri smatram da su jedni od najkomplikovanijih objekata za KGH struku. Prvo su se pojavile na ovim prostorima robne kuće. U Beogradu je 65. godine se pojavila prva robna kuća. To su maloprodajni komercijalni objekti gdje se prodaja radi po principu prodaje sve na jednom mestu. Ekspanzija robnih kuća u Srbiji usledila je 60. i 70. godina. Robne kuće se rade otprilike od 2 do 40.000 metara kvadratnih. Arhitektura robnih kuća bila je otprilike vrlo slična. Sve su one rađene u istom stilu. A sistem prodaje kod robnih kuća se bitno razlikuje nego kod tržnih centara. Kod robnih kuća princip je da je prodaja kompletna na jednom spratu. Znači, jedan sprat robne kuće predstavlja jednu celinu. Prema tome, na svakom spratu robne kuće imate ili zasebno KGH postrojenje ili zasebnu kanalsku mrežu, što je mnogo različito od tržnih centara. Karakteristika fasada robnih kuća tog vremena bila je da je prizemlje urađeno od stakla i ono je uvučeno zbog direktnog sunčevog zračenja. Prednja fasada je delimično od stakla, što vidite na ovoj fotografiji, a na bočnim stranama imate male staklene prozore. Za razliku od robnih kuća pojavljuju se tržni centri ili shopping mall, shopping centar, u zavisnosti od govornog područja, i prvi tržni centar u Srbiji, velike površine, urađen je 2003. godine, ja sam radio taj tržni centar. Danas imamo negde oko 40 tržnih centara u Srbiji, većih tržnih centara. Najveći tržni centar je Galerija Beograd, koji ima 300.000 metara kvadratnih. Međutim, najveći tržni centar koji neprekidno radi u svetu nalazi se u Istanbulu, to je Kapali čaršija, koja je rađena od masivnih debelih zidova, u čijim se gornjim svodovima nalaze prozori za ventilaciju, i ta velika masa građevinskog materijala mnogo je dobra, radi akumulacije toplote i radi peglanja, što bismo rekli, toplotnog opterećenja, naročito u letnjem režimu rada. Problem kod tržnih centara je jedan od tih problema što je prodaja robe u tržnim centrima vrlo različita. Znači, od obuće, tekstila pa sve do kozmetike. Međutim, glavni problem u tržnim centrima je taj što vlasnik tržnog centra finansira u zajedničkim poslovima. Znači, vlasnik tržnog centra finansira u nosećoj strukturi, spoljašnjem uređenju, zatim u hodnicima, toaletima, eskalatorima, liftovima, a sve prodajne, zatim kad su instalacije u pitanju, čilere, razvod vode i vazduha do maloprodajnih objekata, a zakupci investiraju u kompletan sadržaj samog maloprodajnog objekta. Znači, zakupac dobija plafon i patos i 3 betonska zida. Za razliku od tržnih centara postoje i retail parkovi. To su maloprodajni objekti u nizu i u njih se ulazi direktno s polja. Ovaj koncept je naročito zaživeo i dobio na popularnosti nakon epidemije korone koja se pojavila, jer ovde nemamo zajedničke prostore, već, kao što sam rekao, direktno se ulazi s polja. Pošto zakupac lokala, izvinjavam se, direktno finansira u izvođenje radova u lokalima, on može da direktno utiče i na kvalitet KGH postrojenja u samom lokalu. Obično u svim lokalima retail parkova imamo i vazdušne zavese, a dosta se koristi i gas u zimskom režimu rada. Šta je jedan od suštinskih problema tržnog centra? To je određivanje energetskog bilansa tržnog centra. Prilikom projektovanja tržnog centra mora da se napravi takozvani tenant mix, odnosno arhitekta mora da izvrši podelu po spratovima i na samim spratovima određenih maloprodajnih celina. Prilikom projektovanja, arhitektonskog projektovanja, vlasnik centra ne zna ko su budući zakupci. A svaki brend koji tu izlaže robu ima neke svoje određene interne standarde. I u svakom brendu, recimo u prodavnici kozmetike Kiko, vi imate izuzetno jako osvetljenu površinu, ali recimo u brendu Super Dry, tamo imate duplo manju osvetljenost toga prostora. I sad se postavlja pitanje koju električnu snagu da usvoji elektroprojektant. Zatim, u nekim lokalima imate video wall, a jedan video wall prosečne površine ima recimo električnu potrošnju snagu od negde oko 2,5 kW. U nekim lokalima imate i po 6 ekrana. 6 ekrana vuče negde oko 1,8 do 2 kW električne snage. Zatim imate rešetke na ulazu. Manje rešetke troše oko 400-500 vati, a veće rešetke na ulazu u lokal troše i 1 kW. Znači, određivanje kompletne potrošnje električne energije koja direktno utiče na toplotne dobitke je više stvar pretpostavke i ocene projektanta tržnog centra nego samog proračuna. Mi možemo da računamo transmisione gubitke i dobitke, ali šta ćemo da imamo kod zakupaca, to ne znamo. Zatim, tržni centri imaju veći broj ulaza, zatim atriumske kupole kod kojih imamo velike toplotne dobitke i veliki problem predstavlja posećenost tržnih centara. Koji broj ljudi i kako da sračunamo toplotne dobitke od ljudi koji dolaze u tržni centar? Obično se uzima da je 6 do 8 ljudi po kvadratnom metru prodajnog prostora. U ovim objektima uglavnom se koriste u prodajnim objektima fan coil aparati, VSHP uređaji, odnosno male toplotne pumpe i VRV uređaji u zadnje vreme. Projektne temperature su 20, odnosno 24 stepena, a temperature u zavisnosti od sistema date su ovde. Znači, toplotni bilans u jednom tržnom centru se uglavnom usvaja, a delimično se i računa. Znači, tu imamo određenu neizvesnost. Takođe imamo problem da veliki zakupci, odnosno velike međunarodne kompanije, kakva je recimo Zara, španska kompanija, ima godišnji promet oko 7 milijardi eura. Oni kad prave ugovor o zakupu i kad kupe 3-4 hiljade kvadrata, oni traže malo strožije uslove za KGH instalacije nego drugi zakupci. A vi u trenutku projektovanja nemate te podatke. To može da se odrazi na druge zakupce, jer sad vlasnik tržnog centra mora njih da ispoštuje. A njihovi ugovori su jako tvrdi. Da vidimo šta je kvalitet projekta i od čega zavisi kvalitet projekta i izvođenja radova u tržnim centrima. Zakupac dobija instrukcije, zakupac lokala dobija instrukcije od vlasnika tržnog centra, odnosno od menadžmenta tržnog centra. On dobija priključke za sve lokale. Međutim, zakupac je u obavezi, svaki zakupac, da projektuje i da izvede sve radove u svom lokalu. Ako prosječan tržni centar, prosječne veličine, ima 100 lokala, i ako u jednom lokalu imate 6 i 7 različitih faza preko arhitekture, klimatizacije, sprinkler sistema, odimljavanja, vi znači u jednom tržnom centru imate, na njemu radi oko 650 odgovornih projektanata. To je jako veliki broj ljudi koji projektuje kompletan tržni centar. To treba koordinirati, to treba nekako uklopiti, jer često dolazi do preklapanja u projektovanju između projektanta centra i projektanta lokala. Toliko imamo i izvođača radova, jer za svaku fazu u svakom lokalu vi imate posebnog izvođača radova. To može da bude nosioc radova u jednom lokalu, jedna firma, ali on ima kooperante i za mašinske instalacije, i za građevinske radove, i za slabu struju, i za jaku struju, i za šprinkler. Znači, tu se nalazi velika gužva, naročito pred otvaranje. Vreme projektovanja tržnog centra je jako kratko, jer odluke o donošenju izgradnje tržnog centra mnogo dugo traju, jer treba finansijska sredstva obezbediti. I zakupcima lokala ostavlja se 2 do 3 meseca da izvedu, da projektuju sve lokale i da to izvedu. Kanali koji se rade, magistralni kanali koji se rade u tržnim centrima takođe često znaju da budu problem. Ja sam radio u 9 zemalja i isključivo zadnjih 10 godina radim na tržnim centrima i u svakoj zemlji, nema veze da li u Evropskoj uniji ili nije, na istom principu se radi i tu su jako veliki problemi. Ako vi imate 200.000 kvadrata da izvedete, vi ne možete da nađete firmu, ili vrlo teško se nalaze firme, koja može za tu kvadraturu da izvede sve lokale, odnosno da je jedan izvođač, pa se onda uvodi veći broj izvođača radova u posao. Tu kod kanala dolazi do velikih problema, odnosno nadzor nad izvođenjem tih radova. Stručni nadzor bi morao, kao na svakom objektu, tako i novim objektima, tačno da definiše kod kanala kakav je način zaptivanja kanala, da definiše problem šta je to masa, odnosno šta je kilogram jednog kanala. Lako je izmeriti, ali obično tu nastaju problemi sa izvođačima ako projektom nije definisana masa, odnosno kilogram jednog kanala. Zatim, koliki je sloj pocinkovanog lima koji ga štiti i kao problem probnog merenja kanala, ispitivanje nepropusnosti kanala. Da li je ugovoreno ispitivanje nepropusnosti kanala, jer bi takav objekat morao da ima inženjera merenja nepropusnosti koji radi zajedno sa stručnim nadzorom. I na kraju, balansiranje tih kanala moralo bi obavezno da bude. Problem kod tržnih centara su i podzemne garaže. Podzemne garaže moraju da imaju vanredno dobro odimljavanje, odnosno ventilaciju. I dešava se u tržnim centrima, što možete da osetite, da kroz prostor eskalatora, liftova, međuspratnih konstrukcija, da dolazi do prodora dimnih gasova iz garaža i da se u prodajnom prostoru tržnih centara osećaju dimni gasovi. Problem dualnog obrazovanja u zemljama i nedostatak majstora je evidentan, što se normalno na ovako velikim objektima i tekako odseća. Retka je primjena obnovljivih izvora energije na tržnim centrima, jer ovde je suština profit, kao u ostalom u životu. Jedan od retkih primjera je tržni centar Stadion u Beogradu na ovoj fotografiji, gde je na vrhu tržnog centra, koji je jako velik, napravljen fudbalski stadion. Zahtev za kontrolom, rekao sam, da i stručni nadzor, recimo na tih 100 lokala u tržnom centru, mora da obezbedi zakupac. Sad zamislite kad imate 650 inženjera koji mora da kontroliše u jednom tržnom centru te izvedene radove. Ovde je dat samo primer merenja nepropusnosti kanala, jer znate da postoje različite klase nepropusnosti kanala, međutim moramo priznati da u našem poslu merenje nepropusnosti veoma slabo se poštuje i često se ne radi. Eksploatacija objekata tržnih centara je jedan od problema koji nastaje. Zašto? Zato što je motivisanost vlasnika tržnog centra i zakupca lokala različita. Zakup u tržnim centrima se kreće od 25 do 65 eura i onda zato su kratki rokovi izvođenja. Zatim, plaćanje održavanja je takođe jedan od problema koji je primećen. Zakup, održavanje u tržnim centrima, služba održavanja radi samo zajednički deo tržnog centra, a svaki zakupac lokala radi svoje održavanje. To se obično svodi na zamenu filtera. Ne postoji godišnja kontrola ispravnosti rada instalacija u samim objektima, odnosno u samim lokalima. Prema tome, loš rad u jednom lokalu odražava se na rad i na susednim lokalima koji se dešavaju. Vizuelno zagađenje sredine je izuzetno prisutno kod tržnih centara. Zašto? Kada imate tržni centar, kada projektujete svaki objekat, vi dobijate određene karakteristike koje vam za objekat koje vam daje lokalna samouprava. Vama je tu predviđena i visina samog objekta. Međutim, obično na krovovima tržnih centara se postavljaju čileri, kule za hlađenje, kondenzatorske jedinice i ostali uređaji. Pošto strela dizalice ne može da postavi uređaj po sredini objekta, onda se oni obično postavljaju pri kraju objekta i gledaju se sa velike daljine, s tim što ovi uređaji se ne stavljaju na kotu nula krova, nego se dižu na nekih 30-40 cm radi kiše i radi vode i onda na jednom takvom uređaju gde arhitekta i investitor daje velike pare da taj objekat izgleda što bolje, mi sa velike daljine na tom objektu vidimo i čilere, i kule, i kanale za uzimanje svežeg i otpadnog vazduha. To je takođe veliki problem da bi se čiler, recimo, koji je težak 1,5 tonu ili više, smestio na sredinu objekta, taj deo objekta mora da se ojača. Ja bih samo zaključio, pošto imam 15 minuta, da su rokovi za izvođenje radova na tržnim centrima izuzetno kratki. Prosto nema vremena da se oni izvedu. Da je veliki problem projektovanje lokala, odnosno polovine tržnog centra, jer imamo jako veliki broj projektanata. Takođe, veliki kapital, odnosno ljudi koji imaju veliki kapital i prave velike objekte, oni poznaju samo arhitektu. Njima je važno kako će da bude arhitektonsko projektovanje, a sve drugo oni otprilike tumače kao u tehnici je sve poznato. I onda projekti instalacija su prilično podcenjeni i rade se po prilično niskim cenama. A arhitekte, pošto se i oni bave biznisom, traže što jeftinije projektante instalacija, pa prema tome i instalacija klimatizacije, grejanja i hlađenja. Međutim, šta je objekat? Objekat je skup interaktivnih podsistema koji utiču jedan na drugi i ukoliko jedan od sistema nije dobro izveden, taj objekat ne može dobro da služi svojoj nameni. Problem probnog pogona na tržnim centrima je izražen. Zašto? Mi obično danas završavamo, a sutra ili preksutra je puštanje u rad tržnog centra. Kada ćemo da proverimo cevovode na nepropusnost, kada ćemo da proverimo radne tačke mašina, pumpi i ventilatora, kada ćemo da proverimo kondenzat, kada ćemo da proverimo temperature radnih fluida, mi za to nemamo vremena. Jer nije nam ostavljeno vreme za proveru parametara izvedenih instalacija. Organizacija održavanja, takođe sam rekao da je veliki problem, a u stvari sve ovo je trka ka kapitalu i osnovni razlog za ovo je preterana želja za profitom. I ta preterana želja za profitom nas dovodi u situaciju da su nam često instalacije loše. Ovim bi završio. Hvala.
Pazite, malo smo probili vreme, 10 minuta duže nego što je predviđeno. Ako nemate pitanja, da nastavimo odmah sa radom. Zahvaljujem se.
Thank you very much. Very interesting presentation. The second presentation will be done from one of my friends from Greece, Alkis? You are here? Okay, you are here. Okay, the name of, the title of the presentation is Asher HVAC Trainer, Head of Engineering and Menerga Hellas. Thank you, Alkis, please.
Thank you. Good afternoon. My name is Alkis Triantafylopoulos. I'm a mechanical engineer. I'm an ASRA Distinguished Lecturer, and this is one of the main reasons that I came here. I was asked to show you in this short time two different technologies that the ASRA technology is really fond of them, VAV and chilled beams, two different technologies. Keep in mind that the VAV training is a separate training of almost an hour, and the chilled beams is another hour. So we try to combine those two into 20 minutes. We'll do our very best to show both or a little bit of both to this short time. So, great. Excellent, thank you. So VAVs, variable air volume systems. It's a basic thing. It's just a damper. It's a controller. It's not nuclear science. There is a lot of technical background on that. I'm going to show you how they operate, what are the advantages, where we should use them, and where we shouldn't use them. The VAV damper is practically a damper. It's an electrically operated supply motor. We have the blades inside the damper. We have a motor, an analog motor, and then we have a sensor, a control unit that reads analog data and converts them into signals. There are mostly two shapes that you can find across, the rectangular one and the circular one. The circular is usually for smaller flow rates. The rectangular one is usually for higher flow rates. You can see them on both operations of the VAV, pressure independent and pressure dependent. So you can have them operating on both scenarios of pressure dependent and independent, whether this can be your initial design or your after some decisions. The terminal units, the units that you can come across. You have single duct, cooling only, cooling and reheating, duct unit terminals, induction units, parallel flow. So there are a lot of units you will come across. The most common one is the duct, cooling or heating only. And the way they operate, and this is the thing that separates them from a standard damper, motorized damper. So it's not just a damper and a motor that moves a blade analogically. There is a layout, there is a setup with a pitot tube that measures the actual flow rate of the air going through the damper. So you actually know the amount of air that flows within the damper and through the sensors. There's a setup of the sensors. You call this the delta P sensor. And through these sensors, you can actually validate and you calibrate that from the factory actually. And you know in advance how much air flows as a real time. So it's a kind of an airflow sensor on top of a motor sensor. There is an electromotor and a VAV damper, and this motor, only one manufacturer, to the best of my knowledge, makes these motors because there's a lot of data and background info on that. So what they actually do, they take two differential pressure sensors within the duct, within the VAV. They measure the different pressures, and from that they subtract that and they give values, analog values, which then are shown into flow meters, flow rates, cubic meters per hour, liters per hour, and things like that. So the technique, it's kind of a hush-hush thing. No one knows exactly how they do it. It's been open, but no one else has tried so far to integrate this technique from other manufacturers. The mechanical side is pretty simple. It's just a damper. It can be single blade, it can be the dual blade, double blade, three blade, multi-blade, so it's just a damper. It's not nuclear science. There are newer versions of that though. We have been used in the past to have VAVs with a pitot tube that I've shown you before, We have lately more than 4 or 5, mostly European manufacturers, some US as well, that they have eliminated the pitot tube, these blades with inside that they measure with the delta P sensors the flow rate of the air. And they have gone, they made a cone, a plastic cone inside, you can see that from the cross-sectional area over there. And they use the Bernoulli effect in there, and from the Bernoulli effect, they don't need the pitot tubes, the lines, to measure the flow rates. The advantages of that, way better leakage, far more accurate than the pitot tubes. It's also applicable in very lower speeds. Bear in mind that you need to have higher speeds or relatively higher speeds for the VAV dampers to operate. For the Bernoulli thing, you don't need those things. You can have speeds of 0.1 meters per second, and you can also operate on higher air pressures. So they mostly have advantages, probably all advantages, apart from the price. They are more expensive, of course. They are a new equipment. They've been in the market for only, 10 years, unlike the other ones that have been in the market for the last 50 years. So it's a relatively new product in the market, only 10 years old. Most of the manufacturers now have it in their product range, far better than the others. Also, it has also 2 more advantages. It has less pressure drop because it's lacking the pitot tubes. It's more hygienically acceptable. It gets easier, the hygienic certificates like VDI 622, because there are no interference with the air as well. And it makes less noise, exactly because there are no pitot tubes inside. You can see that on the rectangular. I'm showing you also the different classifications that an air damper can get, the European classification an damper can get. And of course the corrosions, you can also have corrosion resistant classes on those, on top of all the other certifications. These are European and not US certifications. I'm showing a very simple application where you have a damper that it's operating as a CAV, as a constant air volume damper. So you have a sensor in the space and you open it and you close it. It doesn't do anything else. Someone goes inside, the sensor opens, you bring fresh air. This could be fresh air, or it could be mixing of fresh air and cooling, or cooling only. It can be worked on both. Either cooling only, heating only for the loads. You can do it for fresh air or for both of those. So what it does, it opens and it closes, nothing else. There is no analog on that, it's on and off. Or VAV. The same motor, the same unit can also work as a VAV, so a variable one, which means that you increase and decrease the airflow rates based on the actual criteria and the needs of the space. So you need more cooling, you open the valve more to allow more air to go inside. You need more fresh air because this is an occupied space like this one here, for example, and you have 50 people in here, so you need more fresh air. You have a CO2 sensor rather than a temperature sensor. The CO2 sensor says, I need more fresh air because more people are here, and the CO2 is being concentrated and it goes to a higher level, and then it gives a signal to the VAV, and the VAV opens, and then it allows more fresh air to be connected. So it's really easy on that. You can drive the VAVs with temperature sensor, with humidity sensor, with CO2 sensors, VOC sensors. So any kind of sensor that can drive those and can produce results for heating, cooling, ventilation only, or all of those combined, humidification, dehumidification, and things like that. How they operate, the basic volumetric pressure characteristics, I'm going to stick on those details, we don't have time for those. And the pressure drop, there are formulas, I will upload all those, of course, that you can download them. Installation, this is the tricky part. For the standard that we all have been knowing for decades now, with the pitot tube, you need a certain amount of space before and after them. You need usually 2 times the diameter of, if it's a singular run, back and forth. You need a laminar flow of air within the VAV in order to be able to operate the pitot tube. So the pitot tube uses a really good, smooth, laminar flow. So you need behind that and after that, usually 2 times the dimension of the rectangular one, of the circular one, sorry about that. Which means that you cannot put it directly after a T connection, you're going to put directly after a line or I don't know, 90 degrees corner, you need to have some space on those. And this is not something we always have on our mechanical installations. For the newer versions, the one that I'm showing you with Bernoulli, you do not have those limitations. You can go absolutely and put them directly on a T connection, on a junk connection, on an angle. So those limitations that you actually have from the old generations, you kind of eliminate them because of the Bernoulli effect that you have on the VAVs that you have shown before. And after you do that, and after you connect your VAVs, the idea is to have also a controller or a fan optimizer. The manufacturers in the past used to call them fan optimizers. Now usually the BMS takes over, so the Building Energy Management System takes over. What it does, it essentially it adds all the flow rates from every single VAV in the building. So let's say I have one air handling unit on the roof of here, and I have 2 or 3 or 4 different spaces. I have VAVs on those. I add all those at the same time. I add the actual flow rate of each one of those VAVs. I make it a total air volume flow rate, and this is transformed into the air handling unit. So the air handling unit knows that adding those 10 VAV units from 2 or 3 or 5 or 10 different spaces, I now need 10,000 cubic meters. So I adjust the fan of the air handling unit at 10,000 cubic meters. I need more, I add more, and this is directly connected, all the VAVs with the controller, directly with the air handling units, the fans, and then everything. And this is why you call them fan optimizers. In the past, there were manufacturers that would manufacture those. Now this has come over to the building management system, the BEMS, to take over and do those things of applications. The latest innovation of those is even smarter VAVs without the Bernoulli effect, with sonic sensors. So eventually you have a sensor that, through sonic sensors, it measures the actual speed of air inside. It measures also the temperature of air inside, and it gives you those data on real time, both on your web interface, on BACnet or Modbus profile, and on Bluetooth. So the newest version, and this is even more expensive, of course, than the Bernoulli, which was even more expensive than the previous one, it gives you the opportunity to be directly connected with the unit, even without opening the roof or the ceiling. So you have Bluetooth on your mobile phone, you can actually get connected to that and do maintenance, do calibration, do whatever you want through your phone. Plus, you also have it connected with your BMS. So this is even smarter, even better, even more expensive, and of course it gives you temperature sensors as well. So you also know the temperature of the air that goes within the VAV. This is a kind of information again, you did not have it from the previous 2 generations. So this is the even further technology. And this is what they look like, the actual connections that you can have, BMS, Modbus, Bluetooth, and everything. Why do we need the VAVs? Why does ASRAIN use them a lot? And usually, lately, Europe tends to use them more and more. They had become obsolete for a few years. Now we see them back in the buildings. It's because more and more buildings are going after green certifications for the buildings, and they do give a lot of value and extra credits if you go and follow the ASRAIN standards, when you adjust your actual flow rates or fresh air flow rates to the actual needs. So do I have enough people here? I have 50% occupancy here. So I only need 50% of the fresh air for this space. The best way that I can do that, if I do not have a dedicated air handling unit for this space, which is very expensive, is to have a VAV connected with the room, following AXA 62.1 and doing all the parameters for the actual CO2. And if you do the standard, and this is why you also need the VAV, following the ASRAIN standard 62.1, you need a V nominal and a V maximum. You need a certain amount of air that you need to go through the VAV, no matter what, and this is the V nominal, this is the minimum amount of fresh air that you need to work on a space, regardless the amount of people that is inside, and it's based purely on square meters of the space without any occupants. And on top of that, you add the fresh air that you need from each individual, and this all has to be considered in the sizing of the VAVs. These are some basic parameters for sizing them. And this is the example. On top of those, we need to take into account when we size them. The ventilation effectiveness, most of our VVs are going to be on the ceiling, so which means the fresh air will not be distributed evenly in the breathing zone. So 99 out of 100 times, the ventilation effectiveness of those is usually at 80%, so we need to take that into account and multiply by a factor of 0.4 or divide by 0.4 to get the actual result that we actually need. Chill beams. Do I have 10 minutes? Less than 10 minutes? How much do I have? Okay, right. The second part, usually combined with VAVs or not sometimes. These are radiant cooling and radiant heating devices. It's kind of the idea of underfloor heating on a coil. So it's a fan coil without a fan. It's as simple as that. It radiates heat, it radiates cold, nothing else. There are two ideas behind that. There are active and passive. This is what you can come across. The active one, the passive one are the previous one. There's nothing like that. It's a simple coil. So air goes inside that. I'm going to show you how it operates, and there is nothing going on in there. The active, you actually have fresh air from your ventilation unit, from the door, from your air handling unit, going through the chilled beam and forcing or kind of forcing a little bit more air to go through the coil. It's a very simple idea. It's a very good design. And it's aesthetically not so bad. I understand that a lot of architects may not like those. They have a lot of pros for the cons of not being as aesthetically pleasing as you would expect. You see them integrated in buildings. You can mostly come across those in office buildings, in airports. A lot of airports have those. In hospitals, they are one of the best ideas for hygienically approved terminal units for cooling and heating. And the idea is that why we should use them? Well, it saves you some capital cost for the main HVAC equipment, and it reduces a lot the amount of energy that you're going to consume on a building. So going with the idea of a chilled beam is because you need a far better result in terms of consumption of energy, and of course the capex, the initial investment is going to be way higher than a standard fan coil. The noise too, I'm going to show that as well. The noise is a parameter that they're going to look maybe later in the future. So passive and active. The passive one, the warm air goes around. It's lighter. It goes up. It reaches the chill beam, and because the chill beam is cold during cooling season, during summer, you see that the cold air drafts inside that with no fans or whatever, and it by gravity goes down. This is very typical radiant cooling application. The active one, you see that you also have a plenum of primary fresh air that goes through the coil, and it kind of uses an induction, and it pushes a little bit more air from the environment and forces it from the fresh air. So there is no fan inside, just the air from the air handling unit, a little bit of fresh air from the ventilation into the space. You force a little bit more air going through the coils. I've done quite a few projects on those, so I'm quite familiar with those. Feel free to reach out to me if you have any spare questions. And I've given a section view over there, what it's looked like with the fins, with the coils and everything as a cross-sectional area. Why do we need them? One of the best ideas, as Johan said, they're very silent. There is nothing moving in there. There's like water only moving there. You have no fans. So there's one of the best ideas you can have for bedrooms. Hotel bedrooms may be the best idea and the best application ever, like zero silent. There is nothing moving other than the air without a fan, without anything. And I'm showing two examples of two chill beams in a bedroom. They suck the air automatically from below, and they reject it on the top, and the cold air will automatically go down without any drafting of air. The basic idea, we have two ideas of how we control them and how we connect them. We can connect the chill beams with cold water. Usually the cold water we use is higher than the dew point of the space, which means that I need a cold water of not 7 degrees or 6 or 7 or 8 or 9 degrees that we usually go from chillers on fan coils. We need usually 14, 15, 16 degrees of water going in the chill beams. The reason why we need that is because if they start condensating, if they start dropping water, we cannot dehumidify with those. So we need the latent load of the space, the dehumidification needs to be done from the ventilation unit. They cannot dehumidify. Unlike fan coil units, VRF, split units, any kind of cooling coils with a fan, these cannot dehumidify. So you need dehumidification from the fresh air unit that is going to come inside. This dehumidification has to be dehumidification of the fresh air plus dehumidification of the space. And you also need higher temperatures on the coil that is beeping the coldness in order to avoid the condensation. Why do you need that, and why is there a benefit on that? It's pretty easy, actually. And let me show you two applications on that, how to connect and what's better for that. Okay? Variable speed drive, you have some specific water valves that are called pressure-dependent control valves, so they're electronic valves, and they will control each one of the load, each one of the chill beams, how they meet, and they will analogically open and close depending on the load. So this means that the pump will have a variable speed, way less energy consumed in that point. If you go with a bypass and a three-way valve, it's easier, it's cheaper, it doesn't save energy on the pumps. The result is the same, it doesn't save energy on the pumps. Maintenance, almost zero. You have no fans, you have nothing. So it's, as I said, it's really low on maintenance, no filters, no consumable parts, no condensate pumps. So in terms of maintenance, it's one of the best things. So not only it's hygienically approved because there are no moving airs and you don't want a moving air, for example, in a hospital, you also have very low maintenance. And let's see the benefits of that. And this is official. You can see them also on the ASRE magazines. What we have come across is that the actual energy needed when we use chilled beams is usually 20 to 30% compared with other methods. The reason is pretty simple. We're skipping all the fans of the fan coils. And I didn't know that, but apparently 40% of the consumption of energy for a building in cooling mode is because of fans and pumps. So the chiller itself, or the heat pumps, or the boilers, or whatever, only consume 50 or 60% for the building. The rest is pumps and fans. So if you take fans out of the equation, you easily save 20 to 30% of energy. That's a huge. Plus, of course, the sound that you have zero sound. The other part is, if you operate your chiller on a higher temperature of water, not 7 degrees, but you make it produce 14, 15, 16 degrees of cold water, or not very cold water, then your chiller will usually work on a way better energy efficiency ratio, the EER and SER, because you force them to work on way better conditions. So you will see easily a chiller operating with at least one, maybe two units more, or 20, 25, 30% higher ERs, less energy consumed from the chillers for the loads of the building. You still need chillers for the ventilation or another equipment to dehumidify the air for the air handling units. But for the chillers of the cooling of the space, for chill beams, your chillers will operate, can operate, should operate on higher temperatures, 14, 15, 16 degrees, and hence you save quite a lot of energy from that. And if you compare those techniques, you also have less energy losses through the piping. So your piping is not 7 degrees and you have somewhere outside of, I don't know, 40 degrees outside. You now have 16 degrees in the pipes and 40 outside. The delta T is way lower, the energy losses are way lower. And this is why it gives you savings based on what you would expect comparing chilled beams versus either VAVs or layer units that we saw in the past in the previous presentation, on even fan coils. Basic pros, low energy consumption, very good thermal comfort. You understand? I didn't say that, this is very important. The thermal comfort in a chill beam is outstanding for cooling. Just like radiant heating, that you have warm ground going up by physics because the warm air is lighter and goes up. When you have a chill beam, the cold air will drop down on itself without even having any fan. So you have literally radiating cooling panels on your head, and this is probably one of the best comfort zones you can get. So if you follow the ASRE 55, you will see that you probably get all scores and all credits from there because it's a really good in terms of thermal comfort. You need way less air handling units and ductwork compared with an all-air unit like the VAVs. And almost low noise. Higher, of course, as I said, higher costs, maybe increased pump energy if we don't do the analog signals, and very, very high importance for humidity control. Thank you.
A very professional presentation. Thank you, Alkis.
Thank you.
Like engineer who design with chilled beams, I recommend that. For the hospital, it's an hygienic solution, and with the low consumption energy you saw, and the low maintenance. And it's very important because in the hospital they don't have money to have maintenance, and this is a good facility for them. Please, in the next presentation. Bravo, Alkis. Thank you.
Hvala. Hvala dosadašnjim kolegama prilikom izlaganja radova, ali bih vas zamolio, koleginici i kolege koji budu prezentovali svoje radove, da se držimo predviđenog vremena i da damo svoj doprinos, da ne kažem da se ubrzamo, jer nam je ipak svima vrijeme, što bi se reklo, četvrta dimenzija. Sljedeći rad je navigacija kroz ključne odnose između napretka sistema za KGH i usklađeno sa propisima u bolničkim projektima. Siniša Soni Vidović.
The big one?
No.
Oh, all right. Dear colleagues, how are you guys doing? Sonny Vidovic, I graduated in this school and I was a half American, half Serbian, so I had to go, right? I had to go home to Texas, and I am a design engineer at Austin. I cover a lot of hospitals, university projects, all about. So in this short time, there's not much of we can do. They already warned us that we have to be short, and I picked a subject that you as colleagues do understand that there's always a conflict between the standards, codes, and the real world. So let's go today as you know what happened with the COVID, and everything's changed, really. So we had to adapt, and we had to kind of do a lot of gymnastics to be able to accommodate all requirements that we as engineers do have right now. So we were forced to do energy efficiency, we were forced to do IQ, we were forced to do the cost long term, we were forced to a lot of million things as a design engineers. And we picked the hospitals because the hospitals are kind of everything, kind of bunch of hodgepodge of every single requirement that we have to do. And this topic is presented as exemplary of what can go wrong. So we do have in the United States, we have a lot of technology experts. We have all kind of new sensors and all kind of helpers how to do, and the peddlers tells us what to do, how to design, and we just follow and we go in the kind of track, and then the problems comes. To expedite this, the Greek colleague just explained the VAV systems pretty well, I think, as the VAVs. And in the good old days with my grandpa practiced engineering, the constant volume system was the god. And I believe that everybody is just like a turning wheel that basically goes from this to this, and eventually we're going to come up to this. Just watch that. The standard that we really struggled with was 170 in the ASHRAE that says no more cross-contamination we want to have a fully ducted return exhaust, and we want to have a dedicated ductor space. We know what happened in the COVID. We start putting the people in the hospitals, and the people were put, it didn't matter what the room is as long as the room was available, so they could go over there, be treated, or die. It was chaos in the hospitals that I worked on. It was really chaotic. And then a lot of complaints came and says, why is these people getting infectious diseases? What is the goal? And then we figured out that we really have a problem with this standard. So the standard problem was with me as a designer. I would get the recommendation as a member. Recommendation number 2 was to have a ducted return. Well, this is pretty much what hospital rooms cost. So this is what they require, really. So if you look at the hospitals, you have ICUs, you have recovery rooms, you have operating rooms and all that stuff. As colleague also before me was talking about business and how much money costs and what has to be done, people start juggling and figuring out what can we afford. The hospitals are built usually by the private people, private doctors who build the hospitals, and the hospitals has 500, 600, 700 beds. So when you're talking about ORs, I can probably afford a lot of good techniques, but if I talk about 500 rooms, how do I do this? So the challenges are, we have a sun, we have a load, we have a whole 9 yards of the factors that come up to that VAV system that presented to us as a God, saver, and energy. So we go ahead and we put, let's say this is a simple that couple rooms here and couple rooms there. Now imagine I'm gonna show you the couple design that I worked lately, how many rooms and how complicated it gets. But just like this, sun goes on east, load goes on east, sun goes on west, load goes on west, VAV picked it up. We have a constant change in the supply. But remember, they only recommended and the standard gave us idea that we have to follow the ducted return without any controls on it. So this is pretty much one floor of the building. This is, and architects are really people that, they come up with the kind of crazy stuff that we as design engineers have to blend in and figure out how this all gonna work. So if you zoom at level 1, level areas, then you go into the simple thing, bunch of rooms with a simple supply, simple return, and simple exhaust. The whole air concept is done by nothing. You just have a duct, you have a ducted return, goes to every single 500 rooms, and that's it. I follow the standard, I'm good to go. Everybody loves me. Well, when it comes to the real problem with it, that things don't balance very well. So, if the return fan, now, how am I doing on the time? This can take forever. So, it's very hard to 15 minutes cover the subject like that. But, okay, return system is the pressure dependent, as they're required by the standard. We know that the supply system is the pressure independent. So how do you marry pressure independent and pressure dependent and hope everything's gonna be okay? If you're a design engineer, you're like, what? What do I do now? And by the way, there is a boogeyman, there's a Joint Commission in the United States that has to accept a building in order for them to operate as a Medicare and Medicaid, which is a government-run program, very, very profitable for the hospitals. And they only look to standards. And they say, you as a design engineer must do the standards. So, as it says there, return fan speed is controlled by tracking on supply. If the supply goes down, the return fan goes down. Now, there is we have, as I said before, temperature change in occupancy, solar load, equipment, everything changes. And the return system is just one fan, one stupid fan, who brings the back fan from the rooms. Now, this is the conflict. If I have 100 rooms over there and my return fan is right here, and this thing is always changing, you understand that whoever is closer to the fan is going to be more affected with the fan than who is farther away from the fan. If I don't have a return from far away, that room becomes a positive. If I have too much return without any controls, rooms closer to supply to return fan will be negative. So I have a hospital that half of the floor it's all of a sudden the negative rooms, half of the floors is the positive rooms. Do the nurses know where to put? Because a patient, let's say the COVID patient comes and the first room is in the positive room, they put the COVID patient in the positive room. Positive room does not have a cross-contamination. It pushes the whole COVID particles out. It's the corridor, spreads to the entire hospital. I gave a whole thing. This is exactly what was happening. It's spread out. You go to hospital, you know you're going to get COVID, even if you didn't have it, just because of this. And we just follow the code. So how do we, and what do we do with it? So we call some balancers people. They come over there, they do this they're the best they can, but every balance is done on the full load. So when they do the balance, they balance the building, everything is perfect. Load changes, things changes, flow changes. You lose the cross-contamination control, you lose everything. So what do? So we start planning, we start talking to the hospital people, we start explaining them if we inherit this kind of hospital without any controls, with a return not control really to anything, we tell them, okay, please, if it's summer mode, you can put the people wherever you want, but if it's winter mode, don't do that. Those who are not infectious, please get them closer to the air handler units. It becomes a really nightmare for them to even understand what we're talking about. And then we said, okay, the best thing is to actually have a controlled return fan, have a VAV system on the return fan. It was like, oh, too much dollars. We're not going to do that on 700 rooms hospital. They accepted to go that way on ORs because they have 10, 15 ORs per hospital, and they could afford that cost. But when they're talking about patients' rooms, they care less. So we started to implement different techniques who are better, who are smarter, and at least give us some control over things. So we created a supply and return tracking based on we put a couple airflow stations on the return area. At least we eliminated the cracks and the corridors, so we stopped that, whatever you guys call it here, PROMA or something, right? Something like that. So we have also put the sensors and we measure the static pressures in every corridor, and based on that static pressure, return damper will modulate in the main duct, but so at least it doesn't pressurize the corridor over the corridor. I mean, I hope this kind of covers the whole thing, the challenge. So the standard dictates one thing, the real world gives you the totally different aspect. If you're in a hospital, hopefully it's done by the real intelligent engineers who do understand how to spread the air around. That's pretty much, is I good? Did I do good? So 15 minutes, I think I did it, right?
Thank you very much. Thank you.
Yeah. Any questions? Who is design? Who's got the problem? All right. Thank you. Oh, right there. All right. Okay.
Thank you. Sljedeća prezentacija je termoekonomska analiza i mjera energetske sanacije jednog objekta autora Ružice Todorović, Sanje Josipović i Milana Gojaka. Zamolio bih, da li su tu? Nema nikog. Hvala. Sljedeća prezentacija je studija slučaja optimizacije GMP u farmaceutskoj industriji životnih nauka, kako se mogu ostvariti uštede energije bez ugrožavanja kvaliteta proizvoda. Conor Murray. Conor, please. Thank you.
The floor is yours.
So, I do. Thank you very much. Okay, 15 minutes?
15 minutes, yes.
Good. Okay, so good afternoon, everyone. Thank you very much for the invitation. I'm going to change tack slightly and talk about life science clean rooms in pharmaceuticals. This comes from a case study with Novartis in Slovenia on work I've done about 2 years ago. This is the only information I can share with you. There's ongoing projects as a result of this, so I want to kind of walk you through. So I always try and take people on a journey, so I'm going to tell you a story. I'm not going to read the slides. I'm going to take you through give you an example of case studies of where we're doing more with less. Both the last speaker and Alkis earlier on talked about VAV and doing things better. So I say to people, we need to do more with less. The background slide here shows you that within the ASHRAE chapters, which I'm a member of, in European region, Ireland is one of those of the number of countries that are there. So we're collaborating together to try and ensure that we do more with less. So I spend my life talking around the world on behalf of ASHRAE about doing more with less air. And the reason for that is because clean rooms generate so much energy in terms of consumption, but they also are over-designed. So in a way, in the last speaker, we've codes. I write ISO standards on behalf of Ireland, and we're talking about new standards. So fundamentally, ISO standards are key to sustainability. We've UN Sustainability Development Goals, and clean rooms participate in at least half of the 17 that are there on it, okay? I talk all the time about going towards a circular economy, and I talk about the 3 R's, which is reuse, repurpose, and recycle. So this case study is in the context of this. For those that are not familiar with clean rooms are typically looked at design with lots and lots of air, but people seem to forget that you need to have the engineering controls, which includes HVAC, as well as segregation in different rooms, pressure cascades, but you need operational controls. So all of these contribute together to give you this. You will find that there's the slides that will be available to you will have much more detail on it than I'm able to go through with you today. But I'm going to talk about this and give you a kind of a journey and a story to try and give you to the end game, which is you can optimize clean rooms. Clean rooms consume huge amounts of energy, and it's moving slowly in the regulated industries where you can get to optimization to meet the regulations, but in doing so, you can actually save energy at the same time. So it also takes into account we need to adopt new technology, apply quality risk management procedures, and we need to optimize performance, and the ISO standards can give us the ability to do that, okay? So the first thing we need to do is the Annex 1, talks about the concept of I'm going to go back one, forgive me on this. Oh, I've gone forward, okay. So can I go backwards on this? Oh, I'm sorry, yeah. Thank you very much. You think an engineer would be able to look at the buttons on a controller, okay? I'm sorry, right? I've got to go back a few steps, forgive me. Oh yes, I was on this one here, which is adopt new technology and optimize performance, okay? So effectively we're talking about in Annex 1, which is what this is based on, it talks about a contamination control strategy. So that's the first thing that came out in 2022. And in that it talks about following ISO standards. The ISO standards in this case is 14644 and -16 is on energy management. And the first thing it says is you tune your airflows, right? We're now looking at effectiveness within this. And in this case study, we measured before and we measured afterwards. We used real-time monitoring, and then we evaluated the data on the HVAC return flows against the airflow patterns within the room and optimized them. And that's what I want to bring you to, all right? So I'm going to skip through some of these, which you can see later on. And these are just guidance. So here is an example of the HVAC system in Novartis in one of the facilities in Ljubljana. And you can see it's quite a complex system. So clean rooms are driven by supply air volume flow rates with airflow patterns to remove contamination, and then you need pressure cascades in the different rooms. So a clean room is one word, but typically a clean room could have multiple rooms, and each of those rooms needs pressure cascade, okay? So this is just showing you where we did one case study within the red zones that's shown there on it, okay? Again, within the time that I have, you can read this later on, but this gives you the areas where they worked on. It just gives the layout of one of the rooms. There's 60 of these type of suites within Novartis in Slovenia. And I'm going to show you how we saved significant amounts of energy. But the fundamental driver in doing the case study was on GMP optimization. GMP stands for good manufacturing practice. So the purpose was to meet the regulatory alignments of the new annex, and in doing so, we applied the ISO standards, and the byproduct was energy saving. So the lesson here in life science clean rooms is you apply the standards and the codes, and if you do your job correctly, you'll actually save energy by default. But you don't come in to say to a regulator, I'm going to save you energy. They're not interested. They're interested in patient safety, their well-being, and the quality of the products. So I'm going to jump straight into here, right? And I'm going to show you a video. Hopefully this will play. And what you're seeing here on one side is, on the left-hand side, is the airflow patterns using airflow visualization. On the right-hand side, the revision of the airflow visualization is based on tuning the HVAC system, which is tuning the supply in the ceilings. They were not the same, they were different. And now if I could try and do this one again. I'll just show you this again. Okay, good. Thank you. But you can see there that this was a commission clean room. On the left-hand side shows you the slow movement of the airflow visualization. And the right-hand side shows them much faster. So the end result on this project was we reduced the air volume flow rates by 30%. We improved the effectiveness of the rooms measured using particle counters. And we end up saving a significant amount of energy. So I'm trying to get you to the important area in this, is that the annual savings you can see there saved 90,000 euros, okay, but they estimated that if they applied that across the 60 odd of these type of clean rooms, they would be saving of the order of 4 million euros a year. Now that sounds like an extraordinary number, but the reality is that traditional designs which were based on tables of air change rates drove over design, and they were trying to keep them under constant volume. So a key part of the last presentation was when you're doing constant volume systems, which is just 24/7, 365, the same amount of air, the same return, over design, to be sure, but you were not enhancing product quality or patient well-being. What you were doing was driving increased costs. So this slide is the important slide showing you that in life science applications, if they're applied correctly, you can actually meet the requirements of Annex 1, which is the new guideline on good manufacturing practice, and at the same time you'll save energy and save money. Now, this is purely only a simple revision and tuning of the HVAC systems, but the future will come into, and I'm going to jump into here. The future is going to be using advanced technology, particularly biofluorescent counters, which will measure the level of autofluorescing units, which indicates a level of microbiological activity. And so we'll now be able to look at actively using demand-based ventilation. So you'll be able to tune your clean rooms dynamically based on predictive quality, where you'll understand the production rates within a clean room, you'll understand the increased emission rates at different stages, and you can actually plan your HVAC systems to upload, to increase the air volume flow rates at certain times, and then reduce them down, all based on measurements of particles and measurements of expected microorganisms. We're also using increasing use of isolators and restricted access barrier units. All of those applying technology, removing people from the space, but we're still using outdated tables of air change rates in over design. Finally, I'd like to say that the future direction, I'm going to go back on this one. The future direction on this is around understanding the current process, understanding what your metrics are to evaluate the performance, looking at using technologies like airflow visualization to show the airflow patterns in how contamination is removed, right? Measure before and afterwards, so you fingerprint first, and then you measure afterwards, and you tune your HVAC systems, and you need to demonstrate to the quality departments in life sciences that you're showing how the value is to product quality based on the metrics, both particle counts and real-time measurements using particle counters based on biofluorescence. This has been achieved in just one project about 2 years ago within Novartis. They're now expanding and extending that execution of the case study into other projects, and they're moving towards that target of 3 to 4 million a year in the future on it, right? Because we're covering so many different things in this conference over the last 2 days, I've tried to give you a very high-level view, but the take-home message is clean rooms have an opportunity to significantly reduce savings, but we need to do it in the life science industry by optimization around the regulations. And the byproduct is, in fact, significant energy savings. The future ultimately will be in demand-based ventilation. And ASHRAE in particular, along with other organizations, are developing guidelines on how to do this in the future. I'm one of those, among many others, writing new guidebooks on HVAC design. And I'd expect those to appear in universities in the next 2 or 3 years, where the youth of our next generation will be designing based on better guidelines. Thank you very much for your time.
Thank you very much. Any questions?
Yeah, and I did that in rapid time, right?
Yes. It's okay. Very good.
Okay?
Thank you.
There you go. I saved 2 minutes, okay? I'm available for any questions later on. I'll be here for a while. Thank you.
Thank you. Sljedeći rad je povećanje energetske efikasnosti i ekonomske uštede u bolničkim kompleksima nakon rekonstrukcije. Autori Đorđe Karić, Vladimir Jevtić i Mirko Komatina. Zamolio bih kolegu da prezentira rad.
Nie, not.
Treća. Ne ova. Treća prezentacija. Po redu.
No. You don't have the presentation?
Yes.
There is?
Yes.
Okay. Let's continue with the next and please install your presentation. Check. Okay?
Okay.
Milana. That's,
Okay.
Historic buildings, sorry. Historic buildings and energy, challenges, compromises, and opportunity for temporary future. Milana Blagojevic. Thank you, Milana. Please, the floor is yours.
Thanks. Good afternoon. Dobar dan svima. I'm going to step a few steps back and a lot of steps aside. You're not going to need it because I'm going to do it in English. I'm an architect, so regarding we were mentioned a lot of times during this conference, so I'm going to maybe eventually answer some of the questions. My presentation today is about historical buildings and how to deal with the restoration of historical buildings that have a lot of restraints in terms of arts and landscape restraints. And we are going to talk about the context, the project goals and client goals, challenges, unforeseen in restoration and compromises, opportunities, and temporary, maybe temporary or less temporary visions. So, the context. I teach at the university, I teach interior design, but I also practice as an architect, and I work with existing building stock, so which is a great percentage of building stock in Italy, and the renovation and the refurbishment of those buildings. Those are mostly listed buildings with different grades of them being listed, which can mean that they have some restraints on their outside features or facades, but they can have restraints on inside features, on technology of restorations, and so on and so forth. The geography and demography of the projects we are working on is mostly, those are villas in Italy that that have been built in various periods of time in the last 500 or 600 years. And also, most of them have been partially or completely renewed or refurbished or restored during those centuries. So we never have the original building. We always get what we get. We have a lot of bodies to answer to. The first of all, Soprintendenza, which is superintendence, which is one of the bodies in Italy that has the most power when we are talking about restraints on the buildings, heritage, and so on and so forth. The legislation frame, the energy performance standards in historic buildings are a little bit of gray area because we have very good standards in Italy about the energy efficiency and energy performances, but when it comes to listed buildings and high category listed buildings, there are a lot of exceptions. So it is a little bit of a gray area. How to pass from client to the owner? I work with private clients that eventually become owners. So it is the passage from the client to the owner of the building is not always smooth, and it's not always easy. And then again, we have to deal, and primarily I'm project management, so I deal with budget and cost estimate of all of those renovations. So I'm not going to talk about one case study. I'm going to talk about 4 projects that I'm currently working on in the past 2 or 3 years. One of them is completed and the other 3 are ongoing. Those are complete residential luxury renovation, single family villa. 2 of them are primary residences, 2 of them are vacation homes in 3 regions, Tuscany, Liguria, and Veneto. And we have the situation where both the building and the gardens are listed. We are, of course, in the Mediterranean climate, and for those 4 projects, the budget range is between 3.2 and 7 million. 3.2 and $7,000 per square meters, which is in 3 cases corresponds to the millions. So one of the villas is in Liguria, Rapallo, which is next to Genova. And we have a really nice, most of the pictures you will see in my presentation are of the outdoors because I cannot put pictures of the indoors. So we are with a very nice views and very nice exposures. This is another project near to Florence. Another one in Verona. So what are the project goals? We need to deliver high-performance buildings, easy to manage, environments and rooms with independent management. This point is very important to our clients because those family houses are houses that are quite big, so they are between 1,000 and 2,000 square meters, and they are going to host a family of 3 or 4 people, so they are unifamiliar houses, which means that they are going to have staff and they are going to have guests, and their staff has different expectations on the comfort, and then they have, their guest might have different expectations on comfort that they have. And then there are a lot of special rooms because normally in the residential house we don't use, I don't know, having a gym or having a wellness area or having a wine cellar or having a lot of special rooms. So in this case we have lots of them, so we have to manage them as independent rooms. Of course, we have a big issue in the last years, which was not the thing when I started working 20 years ago about acoustical well-being. Everybody's getting more and more conscious about the acoustics and the acoustic comfort, and lately also about lighting as a lighting pollution, since we have gardens, but this is another thing. The holistic comfort, which means everybody that we talked about during this conference, about visual comfort, about acoustical comfort, about indoor air quality and thermal contract. Cost effective, even though the client are clients that have the disponibility from the economical part of view, but they want to stay very much, and they're very, very attentive about cost effectiveness of the project. And of course, everybody wants to have the systems invisible. You don't have to see them. So I made a little, let's say, pie chart about forming the budget between 2018 and 2025, about the division in one project, mostly what was the percentage that went to the architectural part of restoration, structural, electric, and HVAC. And more we are moving forward, the cost of the systems on the whole become higher than they were even 7 years ago. And this is one that regards 2024, but I have to say that as we are at the end of 2025, the electric systems now are taking more than 18%, so they are balancing towards the HVAC system, and this is clearly, they're almost half and half. So when we structure the budget, at this moment, we take roughly 40% to architecture and structures and 60% to all of the systems, which are more or less half to the HVAC and half to the electric system. Of course, the compatibility of the standards that are used in the renovations, the measures and the controls. In most of the cases, we are asked to have heating and cooling contemporarily, which means that all of the logic that is connected to the summer and winter regime of running the systems are not that easy to implement. So we go with 4 tubes, which means that one room can have heating and one room can have cooling. So, which means having multiplied the systems and all of the components that we are going to put inside historic buildings and drill the walls and so on and so forth. And then we have to generate spaces, because we are not working with new buildings, we are working with existing buildings. So the space we have is the space we have. And the existing buildings, if they are built in, for example, 17th century, they don't have systems, they don't have most of the times centralized heating, of course. They don't have any kind of cooling, any kind of air conditioning. So they don't have spaces dedicated to the systems. So we need to really generate those spaces. And then we have those, as I said, simple questions and very complicated answers. Because the clients ask simple questions. Can I have 16 degrees in my bedroom where outside is 40 degrees? No, why can't I have that? Because, so we have a very complex answers to give to those questions. So these are, I'm going to run a little bit fast through these plans, but these are the plans that I borrowed from my colleagues, from my mechanical engineer colleagues. And what do we have here? These are some photos for the construction site. So we have, for example, 2 different projects. In one project, we can go and sign all of the traces for the systems. And then we have rooms where we cannot do that, and we can just intervene to a small portion of the room, of the wall, in order to place system inside. So sometimes we demolish, sometimes we do like surgeons. And then when I was talking about generating spaces where to put the systems, we dig under. If we have basement floor, we try to dig under the basement floor in order to put some systems inside. We create gray area from the legal point of view, spaces above corridors, because we can have false ceilings, but those false ceilings cannot be slabs. If they become slabs, we go with the surface, we augment the surface of the building, which we are not allowed to. But if we want to put system above those false ceilings, we have to be able to put a person to go there and to work and maintain those systems and everything. So we do something in between false ceiling and a slab, which is something that remains in a gray area and generates some space where we have the heights in order to place the systems. We break walls, and sometimes we find holes, niches in those walls, and we put the system inside those niches. The picture in the middle is one example of what I was saying about false ceiling that becomes in a way calpestable, so we can put systems above and not have the systems above, for example, in this case, above the bedrooms, but they remained in the corridor, and then we have canalized air going in and outside of the rooms. And in the first picture, here, you see we dig also to put systems. Sometimes one of the projects we have in the same building a completely anonymous ambient room where we can put our underfloor heating and put anything we need. And sometimes we have rooms like this where even putting a single lighting fixture can be a problem, and not only implement the systems. So, what are the challenges? The envelope. So we have a roofing, yes, but we need to use traditional techniques on those buildings, so we cannot use techniques we want to use. We have external fixtures. We can work on external fixtures, so windows and French doors, and put those that are following the standards and that are energy efficient. But we have listed fixtures, so we must put single glass, sometimes blown lidded glass, sometimes having a very, very thin and energy completely inefficient metal frames. We can do horizontal insulation, yes, but we cannot alterate the height of the slabs. We cannot alterate the inner distance to the windows, so we cannot move up with our slabs. So yes, horizontal insulation, but where to put it? We can put vertical insulations, but if we put it outside, we have listed facades, so we cannot. If we want to put it inside, we have fresco paintings on the wall in the rooms. So it's not an option most of the times. And then, yes, we have to have technical rooms, of course, but in the historic villas, there is no space for technical rooms. There is no space for ventilation. There is nothing that regards noise standards or anything. So we have to rationalize, yes, and put passages in the walls that are most of the times in opus incertum, which means the mixture of stone and bricks and cement or whatever you can find inside of those walls that were most of the times not in the original condition, but during the centuries somebody else already dug a hole and put something, and so on and so forth. So a few pictures of one of the construction sites, just to understand, even putting a light switch can be challenging sometimes. We often use the frame of the pavement. We take out all of the tiles of the pavement on the frame, and then we number them, and then we put some systems inside, and then we put them back. And sometimes we need to dig inside the walls that have stone blocks for 40, 50 centimeters big, so not an easy task. And lots of the times when we start doing the most basic demolitions of to start implementing the restoration, we find very creative solutions that were implemented in the 20s, in the 30s, or in the 60s and 70s, where people just cut through the structure. You can see on the second picture, this is the villa near Genova. There is an arch, and they just cut through the arch to put another arch, to put a very ugly decorative feature. Or we find some historical moments of HVAC with very big fan coils, with false ceilings, high 1 meter, that work as plenums, that's giant plenums, and we find lots of stuff. So what are the compromises? Eventually, mostly on financial side of the project, unfortunately for me. We have to do a lot of restoration of pictorial works, so because eventually we have to intervene on the walls, and then we have to call pictorial restorators and to do the restoration of where we put traces and everything. Manual dismantling of flooring frames, cataloging and reassembly, which is both time-consuming and money-consuming. Lots of structural works. More furnishings, more joinery, because we have to work with interior designers and make them draw joinery, woodwork fitted furniture to hide lots of things because nobody wants to see systems. Permits, variants to permits. We have a system of a plethora of permits you have to have in order to work on those buildings, and every time you find something that was not meant to be found, you have to do a variant to permit. Every time you adopt a solution that was not in the design phase, you have to do the variant to the permit, and which leads to prolongation of construction times, reiteration of design phase, and of course, more money to be spent. But also compromises are made on the body of the building and its resilience and future. When we take a building, it has 300, 400, 500 years, which means that it is already very resilient and that it's survived lots of people working on them, architects and whoever client was and the owners and everything. And in some way, they survived and come to us, and we start drilling those buildings with no moral doubts, and putting systems everywhere. Putting systems, putting structural beams to support those systems, and just closing everything. So co-presence we have the doubling of the systems, as I said, because lots of times we have the expectations to have very, very high expectating clients in terms of how what is thermal comfort, co-presence of different HVAC systems in a single building. It is already very complex to have one, but sometimes we have more than one. Increase of quantities of components to support complex programming and managing, because of course everything needs to be programmed and managed. Need of frequent professional technical assistance, energy consumption, and unfortunately solar is not an option in most cases. Not solar energy or photovoltaic panels or any of these, because of the landscape restraints we have, so we cannot put anything on the roof. So what can we do? We have to do all of this while keeping an eye on client's interest, design's interest, because every designer works on its proper design. Building's interest, as I said, we're destroying those buildings. Administrative and urban planning, sustainability of the whole operation, and how are we going to bring it to an end. So I'm not going to go through this. This is one of the things that were asked for one of the villas. We have lots of variation because those clients at the beginning, they don't know what they want. They discover what they want during the works or sometimes where they start living in those houses, so they ask lots of variations and we have lots of problems afterwards. So we have some very not so bad, let's say, technical rooms we found. We can work with that, but we also have some very beautiful rooms that are the finished project. So what are the opportunities? Interior designers' involvement. We try to work a lot with interior designers in order to hide with, as I said, fitted joinery and woodwork, whatever needs to be hidden. Holistic and integrated approach between Mezzonism and neophilia. This is a long debate about having lots of people on the design team that are very much towards neophilia, so everything that is new is good. And then we have, on the other side, a lot of people, mostly architects on our design team, that are very much Mezzoinist. So in the olden days, everything was better, so we need to find a good solution between those. Early budgeting and timing, trying to really understand owners' needs and requirements that sometimes are not that basic. Tailor-made solutions, every project is different, so every project you need to find good solution for that project. Importance of the team of the professionals, and eternal and perpetual work in progress. Experience and learning, so compatibility of the changes with the vision of the future. What is the future? What is our vision of the future? We the mortals look up at the sky. And before, 2 days ago, this slide was an empty slide. What is the, on my opinion, the reason why we come to congresses and conferences like this? It is not to have a catwalk of monologues, 50 works, 50 monologues. It's in order to, of course, besides natural curiosity we have, but it's to have a 3 days polylogue. So to understand, to speak, to see other points of view. So this is something that I wrote in these days, today and yesterday, and it is one of the things that can be after the slide, what are our possibilities, the visions of temporary future, temporary, not temporary, we don't know yet. And so that's that.
Oh, thank you.
If you have any questions.
Quick one.
Oh, yeah.
Do you insulate the houses in the house?
Do we insulate?
The house.
If you make the isolation,
They
the
don't
facade.
have insulation.
They don't have insulation. I have to say that when you have an external wall that is around 50, 70 centimeters, those buildings behave most of the time very passively. When we have the opportunity, we insulate, but it really depends on each case and each building we we work on.
What has happened with plumbing system?
Sanitary. Sanitary water. You have to find space for that also.
Yes.
And then we have
The sewage system and
the sewage system is, well, in Tuscany, there is no sewage system. It's all septic tanks. There is no sewage system
inside.
The sewage system inside. Well, we try to maintain bathrooms where they used to be, so not to move the function of the rooms. And yes, you have to find space for all of those.
Thank you. Thank you.
Avi.
You mentioned that the air conditioning system is based on 4-pipe system with fan coil.
We do mostly underfloor heating and then four-pipe system on the fan coils, yes. To support, no, both cooling and heating to support the underfloor heating.
This is basically
we try when we can to put them outside. No, we cannot put anything on the roof. In the garden, we work with landscape designers, so we try to find together the place where it is less noisy, because we have really acoustic problems with that. And since we can obtain permissions, because you need to do the cement, base for all of the components, for heat pumps, for everything. So we obtain permits for that, and we try to find the best compromise.
Please, we don't have time. Sorry. We should continue.
We'll take it on the banquet.
Thank you. Thank you.
Thank you very much.
Hvala. Thank you. Zamolio bih kolege sa Mašinskog fakulteta i da svoj rad povećanja energetske efikasnosti i ekonomske uštede u bolničkim kompleksima nakon rekonstrukcije autora Đorđa Karića, Vladimira Jeftića i Mirka Komatinu.
Hvala svima. Htio bih prvo da se zahvalim profesoru Mirku i kolegi Đorđe na učešću u izradi ovog stručnog rada. Ja sam Vladimir Jeftić i saradnik sam na projektima pregleda mašinskih instalacija u Ministarstvu za javno ulaganja. Ranije je to bila Kancelarija za javno ulaganje, a od 22. godine je prešlo u ministarstvo, tako da mi u suštini bavimo se sa projektima rekonstrukcija javnih objekata, energetske sanacije javnih objekata. To su uglavnom objekti škola, javnih ustanova i bolnica, između ostalog, pa smo imali iskustva uvezano za, naročito posle korone, smo imali izmenu naših projektnih zadataka, pošto smo morali da to prilagodimo novim uslovima koje je korona donosila sa sobom. Tako da smo ovo što su kolege ranije pričale, morali mi da uvedemo kao neki osnovni postulat u projektima za rekonstrukciju bolničkih kompleksa. Sad, ovde smo hteli da predstavimo uštede koje se dobijaju u toku rekonstrukcija objekata bolničkih kompleksa. Oni su jako kompleksni. Pre svega zahtevaju kontinuirani rad, visoke higijenske standarde, stabilne klimatske uslove i bezbedan rad medicinske opreme. Šta to znači? Kontinuirani rad znači da mora da ima neki backup sistem vezano za grejanje, da bolnica može da u svakom trenutku odgovori na zahtevima što se tiče grejanja, klimatizacije i ventilacije. Što se tiče higijenskih standarda, to znači da se uvode takozvane HEPA filtracije u čistim sobama i u operacionim salama. To podrazumeva te stabilne klimatske uslove koje se pominju, a medicinska oprema koja je sad savremenija zahteva neke dodatne tehnološke zahteve i pre svega uslove ventilacije. Da bi se uopšte moglo doći do projektovanja ovako složenih sistema, morat će da se koriste pre svega više pristup koji objedinjuje više tehničkih disciplina. Znači, to je pre svega mašinstvo, elektrotehnika, građevina, energetski menadžment. Uprkos tome što je početni projektni zadatak dosta opširan, on se kasnije sužava na konkretan bolnički kompleks. Tako da pre izrade projektne dokumentacije radi se tehno-ekonomska analiza sa više varijantnih rešenja. Što se tiče samog efikasnog upravljanja energijom, treba naglasiti da to se najbolje radi preko BMS sistema, gde se kontroliše rad klima komora, znači osvetljenja i automatike rada nad medicinskim aparatima. Tako da, u suštini, sva ova projektna dokumentacija koja se izrađuje mora da pre svega bude pokrivena odgovarajućim standardima. Znači, to pre svega misli se na ovaj AŠE standard 170, koji definiše minimalne zahteve za ventilaciju u zdravstvenim objektima, zatim sistem energetskog menadžmenta ISO 5001, kao i ovi standardi koji definišu parametre unutrašnje sredine. To je ISO 17772 i N16798. Oni određuju unutrašnje parametre kao što je relativna važnost, koncentracija CO2, brzina vazduha i sl. Takođe mora da se uvaži i regulative Republike Srbije, pre svega Zakon o racionalnoj upotrebi energije i Pravilnik o energetskoj efikasnosti zgrada, Zakon o planiranju i izgradnji. Evo ovde je prikaz jedne bolnice u Valjevu koja je novo projektovano stanje. Generalno, otprilike tako izgledaju svi ovi bolnički kompleksi većeg obima. Pošto imamo zdravstvene objekte primarnog, sekundarnog i tercijarnog sistema. Ovde u suštini je sekundarnog sistema bolnice Valjevo. Ovo što je u metodologiji, pre svega urađena je metodologija uporedna analiza bolničkih objekata pre i posle rekonstrukcije sa fokusom na energetsku efikasnost, unutrašnji komfort, pozornost sistema, ekonomsku opravdanost investicija. Znači, mora da se značajni deo potrošnje nastaje kao posledica specifičnih zahteva kao što je rad sterilizacione opreme i kontinuirane ventilacije sa velikim brojem izmena vazduha, rad dijagnostičke i laboratorijske opreme. Ono što predstavlja problem je to što sad mi s jedne strane pravimo uštedu tako što sa pasivnim merama i aktivnim merama smanjujemo potrošnju, a s druge strane uvodimo nove sisteme ventilacije i klimatizacije, centralnu klimatizaciju, onda imamo uvećanje na električnoj energiji, pa onda moramo tu da napravimo neki odgovarajući bilans. Znači tu pre svega uvodimo toplotne pumpe, solarne kolektore, rekuperatore toplotne energije, što može značajno da utiče na potrošnju samog objekta. Studije pokazuju da bolnice troše 3 do 5 puta više nego stambeni objekti po kvadratnom metru, tako da je u Srbiji otprilike ta potrošnja iznosi za bolnice od 400-600 kWh po kvadratu za G energetski razred. Mi smo uglavnom gledali da po smernicama imamo obavezu da projekti koji se odnose na javne objekte budu bar 2 razreda iznad postojeće klase, tako da se u tom smislu dobijaju i veće uštede nego da je po regulativi koja je propisana samo jedan razred iznad. Ovde smo analizirali objekat u okviru kompleksa bolnice Čačak. Sad ću vam pokazati. U okviru te cele projektne dokumentacije predviđene su pasivne mere, pre svega izolacije kompletnog termičkog omotača, zamena građevinske stolarije, a od aktivnih mera predviđena je zamena svih grejnih tela sa ugradnjom termoskih ventila, zatim zamena kompletne cevne mreže sa ugradnjom cevne izolacije, ugradnja kompaktnih toplotnih postavnica sa cirkulacijnim pumpama promenjivog protoka, ugradnja dikter sistema, merenje toplotne energije, a pre svega i promjena toplotnog izvora. Znači, bazno je bila kotlanica na gas koji sada se renovira i uvodi se nova kotlanica na sečku sa back-upom na prirodni gas. U metodologiji su obrađivani parametri vrste radova, površina postojeće novoprojektovanog stanja, potrebna količina toplote postojeće novoprojektovanog stanja u kilovat-časovima, specifična toplotna energija za grejanje i energetski razred energetske efikasnosti. Ovde je dato u tabeli rezultate koje smo dobili, gde tabela 1 predstavlja postojeće stanje. Imamo, znači, objekte koje smo gledali, to su objekti koji su postojeći, koji se rekonstruišu i minimalno dograđuju, pošto za objekte bolnica koriste se pravilnici koji zahtevaju neke izmene u samim prostorijama, povišenje visine kao i dodavanje mokrog čvora, pa je potrebno i da se ti prostori povećaju i time i se radi dogradnja. Ovde vidite da su energetski razviti od C pa do G, znači različiti su energetskog razreda, pa prema tome su i uštede veće ili manje. Ovde, znači, nakon novoprojektovanog stanja, vidimo ovde da se negde uvećava, na sledećem slajdu, negde se uvećava energetski razred sa 4, negde za 1, tako da predstavljene su i procentualne uštede, da vidimo da to ide od 10-11% pa do 80%. Ono što je otprilike prosječna ušteda, to je nekih 65,61%, što pokazuje visoku efikasnost primjenjenih mera energetske sanacije i znatno povišanje termotehnički performansi kompleksa. Eto, to je otprilike ono što smo mi hteli da vam predstavimo. Tu, osim termotehničkih sistema, imamo i druge sisteme koje se rekonstruišu, znači imamo sistem i vodosnabdevanja, imamo i kanalizacijone sisteme i elektrosisteme, ali ovo najviše uštede se dobijaju na termotehničkim FAK instalacijama i otprilike procenjene uštede kreće se od 10 do 80%, pri čemu se najveća ostvari ušteda između 50-70%. To znači pokazuje da ekonomska analiza pokazuje da ulaganje u sanaciju i optimizaciju KGH sistema može biti isplativa u periodu od 5 do 10 godina, u zavisnosti od tipa sanacije i veličine objekta. Ali pre svega mora da se vodi računa o pristupu, sistematskom, multidisciplinarnom pristupu, neophodno za postizanje efikasnih održivih rešenja. Eto, toliko od mene.
Hvala. Ima li pitanja?
Evo pa čisto komentar jedan na ovo. Ja sam Đorđe Karić, direktor Toplane Šabac, također sam član Ministarstva za javno ulaganja. Pored mene profesor Mirko Komatina sa Mašinskog fakulteta i evo dok smo dolazili ovde, pošto smo obojice iz struke, pa mi privatno pričamo o ovim temama, pričamo koji su objekti najbolji za rekonstrukciju. Znači, vi ove procente od 50, 60 ili čak 80% ne možete da postignete u stambenim objektima. Toplana Šabac je sprovodi i dalje projekat energetske sanacije stambenih zgrada na sistemu daljinskog grejanja koji sprovodi u saradnji sa Evropskom bankom za obnovu i razvoj. Neki procenti uštede do kojih mi dođemo su od 20 do 40%. Zavisi od mnogih elemenata. Šta je stvar, šta sprečava uštede je to što ovdje imate centralizovane odluke. Kada radimo energetsku sanaciju stambenih objekata, vi imate problem što imate stanare koji svi moraju da donesu neku zajedničku odluku i ne možete da primenite kompletne mere za uštedu energije. Šta to znači? Znači, oni se u principu dogovore da urade energetsku sanaciju objekta i da urade rekonstrukciju spoljašnjeg omotača zgrade, ali ne možete da ih ubedite da oni urade, ne znam, termostatske ventile. Ili, recimo, stanari sa posljednjeg sprata neće da rade izolaciju ploče prizemlja ili ne znam, ovi opet od dole neće da rade termo i hidroizolaciju krovova. Tako da ne možete da primerite kompletne mere za uštedu. Kod javnih objekata, ovde ne mislim samo na bolnice, nego i na škole i na druge javne objekte, dobra stvar je što imate jedno centralno odlučivanje i možete da primenite sve mere za uštedu energije i da dođete do ovako dobrih procenata uštede. Eto, ne bih više. Hvala.
Zahvaljujem se kolegama. Ja bih samo jednu stvar zamolio. Mi imamo još po programu još pola sata vremena, a imamo 4 rada plus 1 koji moramo da ispoštujemo. Tako da bih vas zamolio da, što kažu, brzo reagujemo i brzo radite prezentaciju. Ja ću najaviti kolegu Draška Kovača sa radom Nivelisani trošak energije i trošak životnog ciklusa u funkciji više kriterijumske optimizacije energetskog sistema hotela koji je rađen zajedno sa profesorom Aleksandrom Anđelkovićem. Pošto je ovo naš kolega, ja ću ga zamoliti da bude jasan i kratak.
Naravno, hvala kolega, trudit ću se zaista da se ubrzam i da ubrzamo cijelu ovu sesiju. Prvo da kažem da na ovoj sesiji danas primjećujem da ima dosta radova koji obrađuju veoma zahtjevne objekte. Prvo smo imali robne kuće, tržne centre, muzeje, pa sad bolnice, to su sve zahtjevni objekti sa aspekta klimatizacije, grijanja i hlađenja. Naš rad se bavi optimizacijom energetskog sistema, a posebni osvrt na KGH sistema jednog hotela srednje veličine koji se nalaze na južnom Jadranu. Inače, ovaj rad je samo dio opsežne jedne analize i istraživanja koji se bavi jednom metodologijom više kriterijumske optimizacije kompletnih hotela na Crnogorskom primorju. Svakako, svjedoci smo porasta potražnje za energijom svih ovih objekata. Vidjeli smo malo pri novim prezentacijama kako se negdje, čak i kod savremenih objekata, povećava potražnja za KGH energijom, a sa druge strane mi nadomještamo, što kažemo, oblačimo zgrade u smislu radimo energetsku efikasnost i u tom smislu radimo i sanaciju krova, sanaciju fasade i doprinosimo na taj način. Inače, kad se radi bilo kakva procjena uopšte ulaganja u neki hotel, vezano sa aspekta ekonomskog ulaganja, naravno to se ne može zapostaviti iako mnogi investitori gledaju samo taj jedan kriterijum, ekonomski aspekt u smislu financijskog ulaganja. Naravno, mi u ovom radu povezujemo jedna ekonomska kriterijuma, a to je nivelisani trošak energije i onog što bi se reklo cjeloživotni trošak neke opreme, odnosno KGH sistema. Bazirali smo se i fokus je stavljen na KGH sistemima gdje smo radili optimizaciju u smislu povezivanja ova dva ekonomska kriterijuma sa dva kriterijuma koje su energetski, odnosno tehnički i ekološki, a to je potrošnja primarne energije i emisija CO2. Ovdje vidite teorijski osnov na osnovu čega smo mi ovdje uradili. Dva ekonomska kriterijuma koji su veoma značajna kod balansiranja između same ekonomije, energetske efikasnosti i ekoloških zahtjeva kako hotela, tako i drugih objekata. To su nivelisani trošak energije i cjeloživotni trošak neke opreme, odnosno trošak životnog ciklusa. Ne bih detaljno ulazio u samu teoretiku ova dva pojma, svakako svako od kolega koji je ovdje prisutan ili neko drugi može da kontaktira i nakon ovoga kongresa da damo pojašnjenja vezano za ovo. Zašto smo se mi opredijelili za ova dva ekonomska kriterijuma? Zato što u razgovoru sa investitorima, odnosno sa vlasnicima hotela, njima je u prvom redu uvijek ekonomije. Koliko to nas košta? Tek možda neko od njih na drugom, trećem, četvrtom mjestu kaže hoćemo ekološke zahtjeve, naš hotel treba da bude zeleni hotel, mi hoćemo da doprinesemo približno 0 emisiji i tako da. Ali to su manji. manji broj njih je takvih. I zato mi sad ovdje integrišemo ova dva ekonomska kriterijuma koji su primjenjivi ne samo za KGH opremu, nego i uopšte za sve termotehničke sisteme i sve druge sisteme koji se danas pojavljuju. Ne samo u tehničke sisteme, nego bilo koje sisteme gdje mi procjenjujemo koliko će neka oprema, odnosno neki objekat ili neka uopšte investicija da nas košta tokom cijelog životnog vijeka, a ovaj dio nivelisani, znači trošak energije, mi izračunavamo na osnovu diskontnih stopa, gdje smo ovdje u skladu sa praksom inženjerskom, koja je od 3 do 7% se računa na 20 godina, uvukli i izračunali za sve ove 4 konfiguracije gdje smo koristili tehnologiju solarnih termalnih panela, fotonaponskih panela, imali smo toplotne pumpe i pogotovo u razgovoru sa vlasnicima hotela, oni traže da imaju rezervnu, ipak da drže jedan kotao na tečno gorivo, odnosno na tečni naftni gas, konkretno na hotel koji smo obrađivali, on radi sa tečnim naftnim gasom i zbog toga smo u ovoj analizi uzeli konfiguraciju koja pored obnovljivih izvora energije, iako je hotel se nalazi na primorju i bogom dan da koristi sunčevu energiju u maksimalnim iznosima, mi to danas nemamo. Nemamo čak ni u okruženju na Jadranu, a pa tako nemamo ni na Crnogorskom primorju. Razmatrali smo 4 konfiguracije. Jedna konfiguracija je kombinacija toplotne pumpe i fotonaponskih panela. Druga konfiguracija je toplotna pumpa plus fotonaponski paneli plus solarni termalni sistemi. Treća konfiguracija je toplotna pumpa i kotao na tečni naftni gas i četvrta konfiguracija je gdje imamo jedan konkretan primjer na jednom hotelu također, imamo toplotnu pumpu, fotonaponske panele i kotao na tečni naftni gas. Šta smo mi radili? Začunali smo za svaku ovu, prije nego što kažem to, ovdje u tabeli su prikazani, samo izvinjavam se. A ja jesam, ali...
Ne, imate veliko centralno dugme i dugme ispod malo.
Aha. Dobro. Aha, okej. Ne, pritisnuo sam ovo, desno sam pritisnuo, ovo, sa strane sam pritisnuo, okej. Samo da ja dođem do ovdje. Mi smo, šta smo ovdje u polaznoj analizi radili? Uzeli smo da diskontnu stopu 5%, vijek trajanja sistema 20 godina i uzeli smo podatke o cijeni električne energije, tečnog naftnog gasa, cijene PV sistema, investicija za toplotnu pumpu, investicija za solarne kolektore i radili smo analizu osjetljivosti gdje smo varirali diskontnu stopu od 3 do 8%, a cijenu ovih energenata, cijena električne energije i tečnog naftnog gasa od plus minus 20%. Šta smo mi tu dobili? Dobili smo kod izračunavanja troška životnog ciklusa za prvu konfiguraciju da je vrlo slična, odnosno vrlo mala je razlika između prve i druge konfiguracije. Treća i četvrta su daleko veće investiciono ulaganje, odnosno trošak životnog ciklusa koji ne ulazi ne samo početna investicija, nego i troškovi operativni, troškovi održavanja, troškovi zamjene neke opreme i na kraju dekomisije. To je sastavni dio ove metodologije. Konfiguracije 1 i 2 imaju najniže ove vrijednosti, s tim što je ova dva povoljnija, malo je povoljnija nego prva konfiguracija, a treća je konfiguracija najnepovoljnija. Vrlo slični rezultati se dobijaju kad se radi i izračunava nivelisani trošak energije, gdje smo izračunavali taj nivelisani trošak energije eura po kilovat satu, pa smo dobili da su opet prve dvije kombinacije najpovoljnije, a treća je najnepovoljnija, četvrta je neka umjerena vrijednost. Emisije CO2 smo također izračunali i šta smo na kraju radili? Mi smo poredili ova dva ekonomska kriterijuma sa ovim kriterijumom, ekološkim kriterijumom, pa smo uparili, napravili smo dva para, gdje imamo trošak životnog ciklusa i emisija CO2, a drugi par je nivelisani trošak energije i emisija CO2. Na ovom grafikonu ovdje je prikazano 4 ove konfiguracije, gdje kaže da konfiguracija 2 da je najpovoljnija, ima najniže vrijednosti cjeloživotnog troška odnosno troška i emisije CO2. Konfiguracija 1 je blizu tog Pareto optimuma, međutim i ona je malo slabija nego ova druga konfiguracija, daleko. Četvrta konfiguracija ima neke srednje vrednosti kriterijuma i treća konfiguracija je potpuno nepovoljna konfiguracija. Sljedeći dijagram je odnos gdje je prikazano nivelisani trošak energije i emisija CO2. Ovdje se opet vrlo slično pokazuje da je odnos, da su ove dvije konfiguracije 2, odnosno 1 najpovoljnije, da je treća neka povoljna, ali ne baš dovoljna, a četvrta konfiguracija najnepovoljnija. Zajednički prikaz na ovom dijagramu ovdje nam ukazuje gdje smo radili analizu kompromisa, gdje kažemo ako povećamo LCC, da li ćemo povećati CO2, da li ćemo povećati nivelisani trošak energije i isto tako emisiju dobiti koje veličine. Radili smo analizu osjetljivosti, ta analiza osjetljivosti, kao što sam rekao, varirali smo diskontnu stopu od 3 do 8%, odnosno cijenu energenata od plus minus 20% i mi smo dobili nakon tih proračuna vrlo slične podatke i rezultate kao što je ovo, što nam dokazuje da je ovo rješenje veoma stabilno rješenje. Na kraj, hoću da kažem da je metodologija višekriterijske optimizacije nekog energetskog sistema, posebno za KGH sistem, veoma je pogodna i povoljna da bi se investitoru dokazalo i pokazalo šta on dobija sa kombinovanjem nekoliko 4-5 kriterijuma. Ovdje smo mi kombinovali 4 kriterijuma, s tim što u opsežnoj analizi imamo analizu gdje kombinujemo 8 kriterijuma. To je dio jednog sveukupnog ovoga. Šta nismo radili? Nismo obračunavali, nismo ulazili u trošak energije, rasvjete i ostalih elemenata. Nego smo samo uzeli trošak KGH sistema. To bi bilo vrlo interesantno u nekom budućem radu, za sljedeće neka istraživanja, da se uvuče kompletan energetski sistem i troškovi na nivou cijelog ovog objekta, u ovom slučaju hotela, tada bi ove cijene, odnosno nivelisani trošak energije bio daleko veći nego kad obrađujemo ovaj sistem KGH. Na kraju da kažem da je metodologija koja ovdje primjenjujem, integracija 4 kriterijuma, odnosno 2 ekonomska, 1 tehnički i 1 ekološki kriterijum kroz jedan vid višekriterijske optimizacije, odnosno Pareto analize, pokazala da konfiguracija koja koristi veći dio obnovljivih izvora energije u današnje vrijeme, što nije bilo prije 20 godina tako, je daleko isplativija i za investitora, i za zajednicu, i za kompletan jedan sistem i kompletno okruženje. Ja toliko, nadam se da sam doprinio da ubrzamo se.
Čestitam.
Hvala.
Može ima neko pitanje, kratko, brzo? Nema. Hvala.
Hvala. Thank you.
Ja sada najavim rad upravljanje energijom i rekuperacija toplota iz otpadnih voda u savremenim zgradama. Vi ste prezenter, izvolite. Rad su prijavili Ivan Vizmeg i Aleksandar Đelković. Vi ste Ivan, pošto Aleksandar znam. Izvolite. Vi gledajte da poštujete malo vreme, samo molim se.
Ja sam Ivan Vizmeg, student na doktorskim studijama Fakulteta tehničkih nauka u Novom Sadu. Rad na koje je zasnovana ova prezentacija jeste upravljanje energijom, odnosno energetski menadžment i rekuperacija toplote u savremenim zgradama. Ja ću pokušati, naravno, što brže da prezentujem srž ovog rada. Stambeni sektor u EU, odnosno prema podacima Europske komisije, zgrade troše otprilike 40% energije, finalne energije i učestvuju sa 36% u emisijama gasova sa efektom staklene bašte. U Srbiji situacija je vrlo slična sa podacima kroz razne analize od 35% ukupne energije, potrošnje ukupne energije. Potrošnja energije u zgradama može da varira u zavisnosti od godišnjeg doba i tipa zgrade, ali ona obično možemo da razložimo na 60 do 70% energije se koristi na grejanje i hlađenje prostora, dok je 14 do 20% energije se troši na pripremu tople potrošne vode. Ostatak energije obično se troši na ostale uređaje, odnosno osvetljenje i elektronske uređaje unutar jednog stana, na primjer. U Srbiji potrošnja ove energije, odnosno specifična potrošnja energije po metru kvadratnom za grejanje i hlađenje prostora u Europskoj uniji se procenjuje na oko 60 kWh po metru kvadratnom. U Srbiji situacija je mnogo gora sa običnim procenama specifične potrošnje od 100 do 120 kWh po metru kvadratnom. Također, u procenu u Srbiji, procene specifične potrošnje vode po osobi u Srbiji je 139 do 150 litara po osobi, dok je u Evropi ovi podaci su slični sa 100 do 150 litara vode po osobi. Po danu, naravno. U javnim komercijalnim objektima ova potrošnja je značajno veća, kao na primjer u hotelima, bolnicama, kampusima. Ove procene su od 300 do 500 litara vode po osobi po danu. Ovaj podatak nam prikazuje mogućnost primjene srži ove teme, odnosno rekuperacije toplote iz otpadnih voda, odnosno otpadnih tokova. Također u ovakvim objektima potrošnja vode je mnogo je predvidljiva i mnogo je više konstantna nego u domaćinstvima. Neki od tehničkih podataka pri razmatranju primjene rekuperacije toplote jednih od glavnih parametara koje trebamo da obratimo pažnju jeste toplotni bilans zgrade, odnosno potrebna energija za grejanje i toplu potrošnu vodu kao i hlađenje. Ukupni koeficijent prenosa toplote, ovo se odnosi na primenjeni izmenjivač toplote, kao i hidrauličke gubitke koji utiču na odabir pumpe, ujedno i potrošnju energije. Tipično rješenje za rekuperaciju toplote jeste primjena izmenjivača toplote koji preuzima naravno toplotu iz otpadnih voda i korišćenje toplotne pumpe za podizanje temperaturnog nivoa ovih otpadnih voda. Neki od najvećih tehničkih izazova jeste zapuštenje samih izmenjivača toplote zbog postojanja raznih čvrstih materija, masnoća i bioloških naslaga. Na ovom slajdu se može vidjeti nekih od parametara za pojedine tipove toplotnih izmenjivača. Preporuke za otklanjanje ovih tehničkih izazova jeste primjena višestepene filtracije, izbor izmenjivača sa povoljnim strujnim profilima, kao i predviđanje periodičnog ili automatskog ispiranja toplotnih izmenjivača. Sistemi energetskog menadžmenta u zgradama imaju za cilj da neprekidno prate, analiziraju i optimizuju potrošnju energije. Oni su definisane standardom 5001 koji definiše energetski menadžment kao ciklus planiranja, primjena mera i praćenja performansi stalnog unapređenja. U praksi arhitekturu jednog savremenog sistema energetskog menadžmenta možemo razdeliti na 3 sloja, odnosno sloj polja u koji ubraja senzor, merače protoka, temperature, pritiska, sloj upravljanja procesima, odnosno regulatori, PLC kontroleri, frekventni regulatori, regulacioni ventili i sloj analitike, odnosno BMS i EMS platforme za vizualizaciju, optimizaciju i prediktivnu kontrolu sloja upravljanja procesima. Jedan od primjera uspješne primjene rekuperacije toplote i energetskog menadžmenta možemo naći na kampusu Border College u Škotskoj. U ovom sistemu primenjeni su izmenjivači toplote naravno sa dve toplotne pumpe ukupnog kapaciteta 800 kW, odnosno po 400 kW. Radni režim ovog sistema jeste temperatura otpadnih voda su oko 7 do 8 stepeni zimi, dok su temperature otprilike 13 do 16 stepeni leti. Izlazna temperatura, odnosno temperatura koja se koristi za grejanje prostora je od 50 do 60 stepeni. Izmereni COP od ovih toplotnih pumpi, odnosno sistema, jeste 4,8 u radu. Neki rezultati eksploatacije ovog sistema jesu 1,8 do 1,9 GWh toplotne energije godišnje, koja pokriva otprilike 95% potreba za grejanjem ovog kampusa i ostvaruje se smanjenja emisije gasova s efektom staklene bašte, odnosno oko 170 tona CO2 godišnje. Neki od tehnologija koje se mogu koristiti za budući razvoj, odnosno unapređenje ovakvih sistema rekuperacije toplote, jeste rekuperacija toplote iz ventilatora, odnosno primjena ERV ventilatora, kako bi se otpadna toplota iz ventilacionih sistema dodatno iskoristila. Toplotna skladišta kojima se energija iz perioda niže proizvodnje i manje potrebe za grejanje prebacilo u periode sa većom potrošnjom, odnosno sa većom potražnjom. Također, primjena modernih toplotnih pumpi nove generacije se predviđa u strategijama Fit for 55 kao Repower Europe, kao jedna od ključnih tehnologija za povećanje efikasnosti i dekarbonizacije u sektoru zgradarstva. Kombinacijom ovih sistema, odnosno rekuperacije toplote, RV sistema, toplotnih skladišta kao i energetskog menadžmenta, zgrade mogu se pretvoriti iz pasivnih potrošača energije u aktivne visokoefikasne energetske sisteme. Hvala na pažnji.
Hvala kolega. Je li ima neko pitanje? Kratko, brzo? Nema. Hvala najljepše. Meni je čast da sada najavim naše gošće iz Rumunije koje imaju rad, one su dragi gošće. Kratka analiza zahtjeva za održavanje sistema KGH ili Short Analysis of HVAC System Maintenance Requirements. Presentation is Mirela Tomsov.
Thank you. I should present a short analysis of HVAC systems maintenance because I think that is more and more important as far as nowadays we are spending about 80% of our time inside the buildings, and new technologies for obtaining more efficiency, energy efficiency building involve using tighter windows and wall systems, which reduce natural air infiltration. This comes with many challenges regarding indoor air quality. So, as I already said, the role of HVAC system became more and more important because they need to ensure both indoor air quality and also thermal comfort. In order to have these functions properly, they need to be correctly maintained. In this way, they could keep running efficiently, we can expand their lifetime, and of course, they could ensure good indoor air quality. The task is quite easy to discover. It's about inspecting and replacing air filters, about cleaning heat exchanger, inspecting and checking the tightness of air ducts, the refrigerant circuits for leaks, the correct setting of temperature, to check the electrical circuit, and of course to make a periodic inspection program. Why these actions are very important? Because in absence of this, there are some hidden parts of this system that we can't see, but they could look very, very worse. So the system components that can collect impurities and spread them in the interior environment are air filters. They can become like this, and it is not so pleasant. It's about air ducts that can collect a lot of debris. It is about heat exchangers, collecting debris, make also the heat transfer became more inefficient. Air supply elements, drain system, and also fan. Yes, and because all these elements are hidden inside the system, it is sometimes it could be very difficult to convince the building owners or managers that they need to spend some money in order to make this, to clear this all element. So it became a budget problem for sure, but I think that main problem is that can become a public health problem. So in order to try to convince the building manager or owners that it is necessary to spend some money, we could put in front that there are many benefits both for occupants and both for building management. For occupants, they should have a better indoor air quality, better comfort, and of course a healthy environment. And for building management, they could obtain a higher energy efficient building, they could expand life equipments, to reduce the operational cost for long term, and for sure they could be in legal compliance. Regarding regulation, we have mainly 3 points of view. There are regulations such as guidelines of technical professionals that refers to design, installing, and frequency maintenance of systems. We have also some standard or European directive that mention some requests about indoor air quality. And we have also the APBD directive, which approach the maintenance from point of view of energy efficiency. Of course, during pandemic period, both public health organizations and also technical association working in field enhanced the importance of ventilation in airborne transmission. A good ventilation could achieve a good indoor air quality. But the problem is that all these regulations are rather advices, not mandatory. So we need to stress again that inadequate environment can affect people, not just subjective perceptions, such as thermal discomfort or unpleasant smells, but it could be a problem, it could give some health problem. There are two main categories. There are some symptoms like eye or skin irritation or dizziness that appear just when people are inside the building and disappear when they leave the building, and they are grouped under the name sick building syndrome. But there are also a group of really medical health problem, such as generated from mold and bacteria or chemical solutions inside the building, and they are named building-related illnesses, and these are really medical dizziness. A recent study, it is a review study that contain conclusion from about 100 of other studies that revealed that there was identified about 100 bacteria and 60 fungal species inside the air conditioning and ventilation systems. And this graph shows the main parts of an air handling unit that and they are presented in percent which part accumulate such as bacteria. In brown we saw the filters, in yellow cooling coils, and in green other parts of HVAC systems. So this study suggests that it is very important to clean this system because they could spread all these bacteria or viruses inside the treated room. As I already said, the maintenance, in absence of some mandatory regulation, many times the maintenance is done reactive. This means we fix a problem only something breaks, and or somebody from the inside complains about the indoor air quality. Another approach of maintenance is to make a preventive maintenance, which means that we need to do some maintenance activities before something failure, and in this way we reduce risk from component breaks, for energy inefficiency, for unplanned shutdowns. And the last approach should be the predictive maintenance that involves installing sensors inside the system in order to anticipate when the service is needed to be done. Of course, it comes with some initial higher costs, but in time we have many other advantages. On the other hand, the influence of HVAC systems maintenance regards on the energy consumption and working parameters is showed in many studies. For example, in a recent study on centralized HVAC systems on a shopping center in Bucharest, showed that after a 6 months period of working in cooling mode without any maintenance, parameters of this system suffered alterations like this. Supplied airflow reduced with 20%, supplied air temperature increased with 19%, which means about 4 Celsius degrees, which in summer could be of an important value. And the energy efficiency ratio fell down with 40%. Another study, it is also a review study, revealed that 15 to 30% of building energy is wasted due to system faults and poor maintenance. So it is very important to maintain this system in good condition, to have a healthier indoor air quality and an energy efficient system. And HVAC maintenance became important also in NZEB buildings, because having a system working in good condition, only having a system working in good condition could ensure the goal of NZEB building. Otherwise, we could compromise this goal, because when energy consume rise, probably building won't be NZEB anymore. So in conclusion, I should suggest to look at maintenance activities like a balance between system performance, occupant comfort, legal compliances, and responsibility for environment. Thank you for your attention. Any question? Thank you.
Thank you. Sljedeći rad je primjena standarda SRPS N15316 u proračunu finalne energije za sisteme grejanja u zgradama. Autori Sandra Kovačević, Branislav Petrović i Miloš Banjac sa Mašinskog fakulteta u Beogradu. Dobar dan.
Potrudit ću se kratko da ispričam šta smo mi to radili. Znači, tema, kao što ste spomenuli, je primjena standarda SRPS iz 2017. godine. Republika Srbija za proračun finalne energije koristi pravilnik o energetskoj efikasnosti zgrada, i to standarde kao što su navedeni 153, 16, 2, 3 i 4 iz 2010. godine. I prema ovom pravilniku se zapravo izrađuje elaborat energetske efikasnosti zgrada. Godišnji gubici toplote sistema grejanja određuju se tako što je neophodno odrediti ukupni stepen korisnosti postrojenja prema pojednostavljenom izrazu. Znači, mi ga pojednostavljamo tako što vrednosti pojedinačnih stepena korisnosti uzimamo iz tabela pravilnika o energetskoj efikasnosti zgrada. E sad, doslednom primjenom standarda iz 2017. godine, mi zapravo gubitke godišnje toplote sistema za grejanje možemo odrediti preciznije tako što ćemo odrediti godišnje gubitke toplote za svaki podsistem, i on se koristi za izradu izveštaja o detaljnom energetskom pregledu zgrade. Što se tiče pravilnika, prema njemu se nalaže da se godišnja finalna energija zgrade računa kao suma navedenih godišnjih potrebnih toplota energije za grejanje i pripremu sanitarne tople vode, zatim energije za hlađenje, klimatizaciju i ventilaciju, osvetljenje i pomoćne uređaje. E sad, za izradu elaborata energetske efikasnosti neophodno je da se podeli, odnosno računamo godišnju potrebnu toplotnu energiju za grejanje i za sanitarnu toplu vodu, kao i godišnju potrebnu energiju za rad pomoćnih uređaja. Na koji način? Pa određujemo prvo godišnju potrebnu toplotnu energiju za grejanje i pripremu sanitarne tople vode, tako što određujemo potrebe i godišnje gubitke. Prvo, godišnje gubitke toplotne energije sistema za grejanje, određujemo ukupni stepen korisnosti postrojenja, za koji sam već spomenula da se određuje tako što se vrednosti pojedinačnih stepena korisnosti kotla, cevne mreže i automatske regulacije usvajaju vrednosti iz tablica pravilnika o energetskoj efikasnosti zgrada. Nakon toga određujemo godišnju potrebnu energiju za rad pomoćnih uređaja, korišćenjem instalisane električne snage uređaja pomoćnih sistema, zatim vremena rada pomoćnih sistema u toku jednog dana i broja dana rada pomoćnih sistema grejanja. Što se tiče izveštaja o detaljnom energetskom pregledu, takođe godišnja finalna energija se računa na isti način, znači potrebno je da izračunamo godišnju potrebnu energiju za grejanje i pripremu sanitarne tople vode i rad pomoćnih uređaja, međutim, sada računamo svaki gubitak posebno. Za 3 podsistema, kada je u pitanju daljinsko grejanje, razdvajamo na podsistem proizvodnje, distribucije i podsistem predaje toplote. Na koji način? Pa posmatramo podsistem proizvodnje i izjednačavamo godišnju energiju na ulazu u podsistem proizvodnje sa izlazom, znači nemamo gubitke. Zatim, podsistem distribucije posmatramo tako što je godišnja toplotna energija na ulazu u podsistem distribucije toplote jednaka zbiru energija na izlazu iz podsistema distribucije, zatim godišnji toplotni gubici samog podsistema i negativna vrednost vraćene pomoćne energije koja je potrebna za pogon pumpi. I poslednji podsistem, u stvari ovde su date formule za navedene gubitke sa prethodnog slajda ovog, a sad sledeće jeste podsistem predaje, gde mi zapravo određujemo na osnovu sume godišnje toplotne energije na izlazu iz podsistema predaje i navedenih gubitaka od navedenog podsistema. Godišnja potrebna količina toplote za grejanje, od nje prvo krećemo i određujemo je prema navedenim elaboratu i izveštaju o detaljnom energetskom pregledu. E sad, oni se razlikuju iz više uglova kada gledamo na koji način dobijamo vrednost godišnje potrebne količine toplote za grejanje, ali ključne razlike jeste što se elaborat energetske efikasnosti radi prema stepen danu grejanja, dok se izveštaj o detaljnom energetskom pregledu radi prema srednjim mesečnim temperaturama spoljašnjeg vazduha. Još jedna od bitnih razlika jeste drugačiji pristup određivanja koeficijenta transmisionih i ventilacionih gubitaka toplote. Dalje, kada odredimo godišnju potrebnu količinu toplote za grejanje, neophodno je odrediti godišnje toplotne gubitke sistema za grejanje i navedene potrebnu energiju za rad pomoćnih uređaja i na taj način određujemo godišnju finalnu energiju sistema za grejanje. Primenjen je proračun i za izradu elaborata i za izradu izveštaja o detaljnom energetskom pregledu za 2 objekta. Prvi objekat je Zavod za vrednovanje kvaliteta obrazovanja i vaspitanja u Beogradu. Kvadratura je oko 1500 kvadrata i u pitanju energetski razred D. Dobijene su vrednosti za godišnju toplotnu energiju za grejanje objekta od oko 106.000 kWh godišnje prema IDEP-u, znači izveštaju o detaljnom energetskom pregledu, a ako uporedimo vrednosti prema elaboratu i IDEP-u, dobijamo različite vrednosti godišnje finalne energije. Možemo vidjeti ovde, neću se sad zadržavati, ali i gubici toplote su različite vrednosti dobijene. Jedino je godišnja potrebna energija za rad pomoćnih uređaja ista jer je isti proračun. Što se tiče drugog objekta, u pitanju je Geološki zavod Srbije, kvadrature oko 4.500 kvadrata, znači veća je kvadratura, i energetskog razreda E. Za njega je dobijena godišnja potrebna toplotna energija za grejanje od oko 600.000 kWh godišnje i opet kada uporedimo vrednosti elaborata i IDEP-a, godišnja finalna energija se razlikuje i sada ćemo vidjeti uporednu tabelu gde je upoređene su stvarne vrednosti potrošnje objekata, objekta broj 1 i broj 2, u odnosu na vrednosti koje su dobijene iz proračuna prema elaboratu i IDEP-u i ovde možemo vidjeti da su odstupanja najbliža su zapravo prema IDEP-u, odnosno ovom detaljnijem proračunu o detaljnom energetskom pregledu, dok prema elaboratu vidimo da postoje malo veća odstupanja, tako da je moj zaključak da finalna energija za grejanje prema izveštaju o detaljnom energetskom pregledu je dosta detaljniji i precizniji metod proračuna i da mi preko tog metoda proračuna zapravo dobijamo vrednosti finalne energije koje su dosta bliske stvarnim vrednostima, što nam je i cilj, da najbolje pretpostavljamo koliko naša zgrada troši energije. Hvala na pažnji, nadam se da sam...
Hvala, bravo za mladu koleginicu što je bila vrlo efikasna.
Hvala puno, hvala.
We arrive at the end. Yes, the last presentation. No, it's not last, sorry.
Professor Doboshi, floor is yours.
No, it's not mine. No, it's okay.
Ja sam se prijavio u zadnji trenutak, zato nisam u programu.
Is it possible now because it is not put in the program?
The paper, okay. Yes. And it will be after our presentation. Okay.
Sad sam ja na redu ili?
After.
Okay.
Fotografiju jednu, pošto ja idem na večer.
Pa slike.
Okay, we expect. It's not the last presentation, but let's say we invite Florian Tamas Negruț from Polytechnica University of Timișoara to introduce the paper Integrating a Building Management System within a Student Housing Complex. This is a work which in my team we put in function this year. It's a student's residence. And we make the analysis how to improve the energy saving in this building. Florian, you have the floor, please.
Thank you very much. Tonight I will be presenting our work on integrating a building management system within a student housing complex. The presentation will take us through an introduction part, building an HVAC system description, the building management system, a building energy simulation using VABI elements, results and discussion, and of course conclusions. As an introduction, of course, everybody talks about BMS, but what is it exactly? The building management system is an integrated system that remotely monitors and controls a building's installations. What kind? HVAC, heating, ventilating and air conditioning, lighting, water, electrical, high voltage, low voltage, and fire protection. How does it do that? It uses sensors, controllers, and centralized software to monitor thermal comfort, air quality, and equipment operation. Why is BMS important? Well, buildings are responsible for about 40% of the total energy consumption, and the residential sector generates around 6% of the CO2 emissions. BMS integration is essential for the development of smart buildings, combining automation with digital technology for increased performance, efficiency, and comfort. Now, let's get towards the building of the case study. The housing complex is located in the student campus in Timișoara, and it's managed by the West University of Timișoara. The building has the following layout. It has a basement that houses the underground parking and technical spaces, notably the cooling plant and the water supply. At the ground floor, we have a kindergarten with independent access and utilities, and floors 1 through 6 are basically the student dorm rooms, notably 222 rooms, each equipped with 3 beds, 3 office desks, and a private bathroom. Each floor has a shared kitchen and laundry area. And the last floor, the 7th floor, the setback floor, is equipped with a study room and a gym, and also technical spaces, serving the heating plant, air handling unit, and the cooling tower. Turning to the HVAC system architecture, the kindergarten from the ground floor is equipped with a radiant floor heating system, which ensures uniform temperature distribution and increased thermal comfort for occupants. For cooling, fan coils are used, allowing localized and rapid thermal adjustment. Ventilation is provided by a dedicated air handling system, completely independent from the rest of the dormitory building, consisting of 8 heat recovery units. The dormitory rooms are each equipped with a 4-pipe fan coil unit integrated into the ceiling, controlled by the room thermostat. The centralized ventilation system supplies fresh air through the fan coil plenums, ensuring adequate fresh air intake. Stale air is afterwards extracted through the bathrooms via the centralized ventilation system. The heating and cooling plant, the thermal energy is produced by a plant located on the top floor, equipped with 2 condensing boilers, each of a power of 650 kilowatts, running on natural gas. The domestic hot water is prepared with the help of 2 heat exchangers, one connected to the boiler circuit and the other to the solar circuit. The solar circuit is comprised of 32 evacuated tube collectors with 15 tubes per collector, and the domestic hot water is stored in 2 buffer tanks, each with a capacity of 5,000 liters. The building's cooling system is comprised of a centrifugal water-cooled chiller with 1,200 kilowatts of capacity installed in the basement. The cooling tower is situated on the 7th floor and is used to dissipate heat from the condenser circuit. Here you can see pictures from the setback floor. Notably, in the first picture we can see in the background the 2 condensing boilers and one of the heat exchangers, and in the second picture the 2 buffer tanks for storing the domestic hot water. In this picture we can see the technical room from the basement, comprising of the water-cooled chiller. And here we see the cooling tower and also another picture from the basement, from the cooling plant. The air handling unit is also located on the 7th floor, and it has a total flow rate of 38,000 cubic meters per hour, a heat recovery system using an intermediate fluid, 100% fresh air intake for superior indoor air quality, and of course its fans are equipped with frequency converters for precise airflow control and adaptation to occupancy level for improved energy efficiency. These are the pictures from the air handling unit room. So let's move now to the building management systems interface. It provides a centralized monitoring interface that provides real-time access to all monitored and controlled systems. An integrated platform for viewing sensor data, equipment status, and also alarm notifications. Its main role is to transform the operation of the HVAC system into an intuitive, easy-to-use, structured, and efficient control environment. We also have dedicated BMS pages for monitoring and control the HVAC and energy systems, live information, interactive elements, and operation diagrams. This is the main navigation page. We can easily select what level we want to monitor or control its temperature on, with easy access to the cooling plant, heating plant on the bottom right corner, and of course the air handling units on the bottom left corner. This is the page. Let's say we enter on the 5th floor. Here, with numbers 501, 502, and so on, we have the numbers, the student dormitory rooms. We can see the set points. Let's see if I can... No, not really. Okay, so with a gray, looking at room 501 with a gray reading, we have 24.3 degrees Celsius. That's the actual temperature in the room, and with bold text, the 24 is the set point. When we click on a certain room, we can see more details, also the exact temperature, humidity, the presence type. We can also take that into account if there is a student present in the room or if there's no one in the room, and also, most importantly, the status of the fan coil unit. In this room that we see, the 505 room, the temperature is 24.4 and the set point is at 24, so the fan coil unit is switched off. Continuing, we have the heating plant page, which can be configured in 2 versions, visualizing temperatures and also visualizing pressures for each circuit. On the bottom left corner, we can see the 2 condensing boilers, and on the central part, we can see each circuit and each temperature for each circuit. So we have the circuits for the radiators, the fan coil units, the heating coil of the air handling unit, and so on. And on the right side, we have the 2 buffer tanks for the domestic hot water, and we monitor the temperature at the lower part of the boiler and at the upper part of the boiler, so that we can control accordingly the recirculating part of the hot water recirculation part. Moving on to the cooling plant page. Here, as before, we can see pressures and temperatures for the centrifugal chiller, and also the status of the cooling tower and its rotational speed. Here we have the air handling unit page, which is very intuitively comprised. We can see that the cold, on the bottom part, the cold air enters at 3 degrees. It passes through the intermediate fluid heat recovery system. And we can see on the top right, we have air coming out of the building at 24 degrees Celsius. And after the heat recovery system, it drops down to 16 degrees. So basically, we gain, through heat recovery, we gain 8 degrees, improving energy efficiency and basically consuming less energy to heat up the air to the set point, which in this case is 22 degrees, as we can see in the bottom right corner. Now moving on to the building energy simulation part, the objective of this energy simulation is to evaluate the BMS impact on energy performance and indoor ambience. The tool used was Vabi Elements, which is a professional simulation platform for designing and optimizing energy-efficient buildings. The simulation capabilities include detailed analysis of dynamic energy flows, assessment of indoor comfort parameters, modeling interactions between systems under varying climatic and operational conditions. We analyzed 2 scenarios. Scenario number 1, the reference one, without BMS. In this scenario, the following operating schedule is taken into consideration. The dormitory rooms are considered to be occupied for about 14 to 16 hours out of 24. 5 days per week, the temperature is set at a comfortable level, and 2 days per week, the temperature is set at a lower level, correlated with a lower occupancy level over the weekend. And for the second scenario, the optimized one with the BMS, in this scenario, the BMS operating schedules are dynamic since they are linked to occupancy levels. So the following hypotheses were taken into account. The students are away between 8 hours and 1600 hours. After 4 o'clock, the occupancy level starts to rise, simulating students coming home from either work or classes. On Fridays and weekends, the occupancy levels are smaller, simulating the students going home or just being away for the weekend. These are some snapshots from the Vabi Elements software, in which we had to build the building's architecture in the software as to visualize it more easily. And here we can see the gas use per area and the energy use per area. These are some nice schematics that the software allows us to visualize to make a better idea of the mentioned consumptions. Here in this table, we have centralized the data with and without the BMS. It is notable and obvious that in the second scenario, the total energy use is lower than in the no BMS scenario. But what is worth mentioning, and on the second line, we have each category, like heating, domestic hot water, cooling, fan pumps, and controls, lighting, lastly. You would normally expect a general loss of use of energy, global reduction of energy use, but the BMS actually really optimized how the lighting and cooling system and also the heating system works. And the most amount of difference, what made the difference, is the lighting. In the non-BMS scenario, lights are just being left on, maybe by accident, or they're just on all the time. With a BMS using presence sensors and optimized schedules, we can really cut down on these costs. And as I said, a key observation, the annual energy demand for heating increases in the second scenario with the BMS, even though the total primary energy consumption decreases significantly. Well, why is that? It kind of seems counterintuitive. Well, without BMS, the inconsistent operation and periods of insufficient ventilation led to an actual thermal load lower than the design load. With the BMS, airflows are precisely regulated according to design, are modulated based on occupancy and CO2 levels, thus increasing the heating load of the outside air. Reduction of and obviously the reduction of internal heat gains, the BMS optimizes the operation of lighting and equipment, leading to lower internal heat gains, which increases in turn the heat requirement. In conclusion, the increase in heat demand is a normal effect of strict ventilation control and internal efficiency improvements imposed by the BMS. Strict temperature regulation in BMS control spaces leads to reduction of overheating and underheating, improves thermal comfort and more stable indoor conditions, and to the elimination of accidental drops below the reference temperature, a phenomenon present in buildings without control, which normally leads to a seemingly lower heat demand. What's the impact on energy and performance? The simulation confirms the efficiency of the implemented technical solutions, and the results are also validated by the Energy Performance Certificate, which places the building in an adequate energy class. So, what are the conclusions? That the integration of a BMS within a student housing complex highlights the positive impact of advanced automation technologies on energy efficiency, operational performance, and indoor ambience. VABI Elements Energy Simulation provided a detailed quantitative analysis. The increase in heating demand is associated with more precise ventilation and strict thermal control. The reduction of internal heat gains contributes to this phenomenon, and the total energy balance remains favorable in the BMS scenario. And the overall conclusion is that a building management system improves system coordination, enhances energy performance, and optimizes occupant comfort, confirming the benefits of its implementation in modern educational buildings. Thank you.
Question? Thank you.
Thank you very much.
Thank you, Florian.
Hajdemo, Aleksandre. Aleksandar Gerasimovski. The name of presentation is Energy Efficient Systems for Greenhouse Heating.
Dobar dan, hvala vam puno.
Dolazi iz Skoplja, ili tako?
Ja sam iz Mašinski fakultet Skoplje. Tu smo došli sa grupa studenata.
Sve znamo.
Pozvani od SMEITS i jako smo zahvalni što su nas ovako prečekali kao pravi domaći.
Bravo. Hvala i vama.
Meni je 5. godina da učestvujem na KGH kongres i nadam se da ću svake godine da bez promaše da učestvujem tu. Pokušat ću, iako je prezentacija na engleski, zato što smo tu većinu od Srbije, Makedonije i Crne Gore, mogu da pokušam da pričam na srpski, tako da u redu.
Ti je lakše na engleskom pričanje?
Hoću, čev mi je da pokušam na srpski da pričam. Hvala. Naslov ovog rada je energetski efikasni sistemi za grejanje oranžerije. Mogu da koristim daljinski da menjam? Hvala vam puno. Predmet ovog rada su energetski efikasni sistemi za grejanje oranžerije koje su sa jednostruki i dvostruki sistem cevima i koji koriste dve vrste energiju za grejanje. Jedna energija je energija iz toplotne pumpe, to bi bila kao skuplja investicija, ali ta bi koristila izvor od geotermalne energije ili kao toplinski izvor isto također može da koristi i otpadne toplote iz neki industrijski proces i ova toplotna pumpa bi generisala jeftine energije, a druga vrsta izvora energije bi bio neki električni grejač ili mali kotao, mali gasni kotao koji bi bio kao jeftina investicija, ali bi generisao skuplje energije. Ideja ovakve kombinacije sistema je da se pokrije bazni potrebe energije sa jeftinom energijom, a vrhni potrebe energije sa skupljom energijom, ali u manju količinu. Cilj ovog rada je da se napravi neka uporedna analiza na ovi sistemi grejanja i razmotrene su 4 vrste sistema, jedan sa jednostruki cevni sistem i 3 sa dvostruki cevni sistemima i upoređaj je napravljen sa korišćenjem toplifikacioni dijagrami i specifično napravljeni dijagrami za ovi 4 vrsta sistema koji su razmotrene tu i uporeda je između različiti odnosi na toplino-izmenjivačkim površinama i različiti odnosi na toplinskim kapacitetima. Glavno za vizualno prikazivanje rezultate koristi se šeme ovih sistema, koristi se toplifikacioni dijagram što je skroz na desno prikazan i taj toplifikacioni dijagram je specifičan za naše makedonsko područje i srpsko isto također, gde specifično je to što se pojavlja takozvani pik potrošnje energije u jako kratkim periodima i zato ovako izgleda. Na kraj ove prezentacije u zaključci prikazana je jedan izvor na podacima koji može se koristiti da se napravi specifičan toplifikacioni dijagram za neki specifičan grad gde bi se projektovali ovakvi sistemi za grejanje oranžerije. To je na kraj prezentacije prikazan. Ovaj software BIZ Jel mogu da menjam sad? Naročito sam preskakao do kraja prezentacije. Do ovaj posljednji slajd. Ovaj software BIZ-E može svako da nađe. Može da se koristi za dobijanje podacima, za da se konstruira specifični toplifikacioni dijagram za specifično područje. Ovdje ima podaci za svaki grad koji ima aerodrom, ima za Beograd, ima i za Skoplje i ako se koristi taj deo za satovna analiza, mesečna pretplata je 30 eura i ovo je jako dobar softver. Pored to što se koristi da se konstruiše toplifikacioni dijagram, može se koristiti za neke energy management systems analize, za da se konstruišaju ove baselines za upoređivanje potrošnje energije u odnos na toplina potrebna za grejanje ili hlađenje sa korišćenje heating degree day i cooling degree day. Tu su besplatni heating degree day i cooling degree day, a satovna analiza se doplaća. Sad, izvini, opet sam... Na drugi slajd. Znači, razmotrena su 4 vrsta sistema. Ovo je opšti slučaj za sistem za grejanje sa dvostruki cevima, gde energija se dobija i od geotermalna topla voda, i od toplotna pumpa, i od kotao ili električni grejač. Izbor toplotne površine za toplinu izmerivača je kompleksan zadatak i ovaj rad će pomoći projektantima da izaberu ono što je najzgodnije da se izabere za taj specifičan vrsta oranžerije. koliko veća površina odaberemo, toliko je skuplja investicija, ali tako dobijamo bolji CO2 toplotne pumpe, a i dobijamo više energije, iskorištavanja energije od geotermalni toplotni izvor. Prvi slučaj je jednostruki sistem cevima, znači sistem za grejanje sa jednostrukim sistem sa cevima, gde ovaj bazni generator toplote, što je sa toplotne pumpe, radi do neka umereno niska temperatura, do 2,5 stepeni, i onda se gasi potpuno i prebaciva se na vrvni generator toplote. Zato ovaj sistem je najjeftiniji kao investicija, ali zato je najmanje je dio energije koja je od jeftini izvor toplote. Može se vidjeti tu u ovim tačkima da veći deo od energije je pokriven sa vršnim generatorom toplote, a samo možda 40% je pokriven sa baznim generatorom toplote. Pritom date su i temperaturne uslove rada. Vrvni generator toplote radi sa režimom 90-70, a ovaj bazni radi sa 55-45 stepeni. Sad još ove tri sisteme što su sa double circuit system, ali sa dvostrukim cevima, ovi su skuplji sistemi. Znači ovi su isti kao na slajd broj 1, izvini. Dobro. Znači ovi double circuit sistemi su ovako ovdje prikazane. Znači, ima jedan krug cevi za vrvni generator, jedan krug cevi za bazni generator. To je gore desno, taj sa ventilima što je prikazan tamo. Znači, ovi imaju prednost, skuplji su, ali dobre su zato što može da radi istovremeno i bazni generator i vrvni generator. Tu je prikazan na toplifikacioni dijagram, ovo je sa plavim i crvenim štraftama. Može da vidite gde bazni generator može da radi sve dok ne se postiže ta nadvršna projektna temperatura, što je za Skuplje minus 15 stepeni. Kad je nadvor minus 15 stepeni, onda full radi sistem sa pik generator toplote, što je sa crvenim ove šrafura. Ovaj sistem je dobar, još bolji od njega je ako projektovamo sistem tako da površina je toliko velika da može svu energiju koju može da se pokrije sa baznim generatorom, da se pokrije sa baznim generatorom, znači mi uložimo u toplotno, u površinu za prenos toplote, sve pokrivamo što možemo sa baznim generatorom, a to vrvno pokrivamo samo sa malu površinu za izmenu toplote, ili ako se radi za električni grejač, onda nema, znači površina A pik je 0, odnosno ne treba nam površina za izmenu toplote. I zadnja analiza je sa kombinacija gde 0,8 od potrebna površina za grejanje je za bazni generator, a ostatak je za vrvni generator. I ovde od desno, ove dijagrami su jako korisni za odčitavanje koliko za različite nadvršne temperature, koliko nam pripada na površina nam pripada za bazni generator, koliko nam pripada za vrvni generator. Tu dijagram je od desno, nisam pomenuo, na svaku kombinaciju ima dijagram od desne strane gde sa isprekinate crte prikazan je toplinski kapacitet, a sa crtu tačku je prikazana toplotna površina ovde na desne strane. One su jako korisne za da se može se odčita kapacitet i površina za prenos toplote. Zaključak je da ovi podaci u ovom radu što su izložene, tu su date različite površine za izmenu toplote za različite kapacitete na ovaj bazni i vrvni generator. Zaključak je to da ovaj rad može se koristiti za optimalni izbor na cevni sistem za grejanje na oranžerije, a može i za neke druge potrebe. Hvala vam na pažnju.
Ako nema pitanja, ovo je kraj našeg današnjeg druženja. Ja ću da vas informišem, hvala vama na strpljenju i na pažnji, i da vas informišem da je tokom prezentacija bilo prisutno 48 plus minus 5, koliko sam ja brojao učesnika. Hvala vam najlepše, jedan put svima.